We're going to have one keynote talk which starts at 11, and then we're also going to have 14 contributor talks. Okay, so these are the regular talks. Each will be 20 minutes. So we're going to have one poster session. The poster session starts officially at 4 if you look at the program, but it's going to take place well, where we have coffee, basically. So we're going to try to start actually as soon as the coffee break starts. So there will be probably some time to set up the posters and so on. All right. So at 3:30 we go get the coffee. The people presenting the posters, they're going to set up, and we start as soon as possible, because otherwise 30 minutes can be, well, a little short. So the lunch will be here. So well, wherever is the coffee area. But unfortunately, we're going to have 10 minutes less compared to many of the other workshops. This is a little unfortunate, so sorry about that. I just want to say that it's not my fault. Okay, there was a miscommunication. As you see, it's like a very big event. There's like many emails going around back and forth. So there was a miscommunication. I am not responsible for the miscommunication. But, well, these things happen. So actually the original plan here was to finish at 6, okay? But then this was not actually possible, we were told, and that was the miscommunication, because the workshop can only finish at 6 on the weekend. And that was the miscommunication, basically. So now we had to figure out a way to, well, fit something that would, we were supposed to finish at 6, so now we have 2 extra talks. How do you fit them? And this is what we came up. Okay, 10 minutes less for a lunch break, and it's not that bad, I guess. All right, so we haven't planned any official workshop dinners, but of course you can just organize between yourselves if you want to have lunch with someone. Again, so our keynote, or our invited speaker, is Christophe Charton. So he's going to speak at 11. He's still not here, but he's, I think, on a train at this point, so he'll make it. Okay, the French trains are not that bad. Yeah, I think they're pretty good, actually. All right, now time for some statistics. Well, the statistics are usually done at the end of the event, but because of what I just said, you know, there's no time for a closing address, so the opening address is also the closing one. All right. So we had 35 submissions this year, and actually this is actually not bad. I mean, for a workshop which is also very specialized, 35 submissions, I think it's pretty good. 14 of those were accepted for a talk, and well, we can see that those were on pretty diverse topics, covering everything from cost analysis, operational semantics, denotational categories, type systems, circuits, optimization of circuits, and so on. So it's really a nice range of talks here. 17 were accepted for a poster presentation. Well, out of those, 7 decided not to present their poster, but we are going to have 10 posters here. And well, as with any other conference, you know, what gets accepted for a talk, what doesn't get accepted, or gets, let's say, demoted to a poster, it's a little subjective sometimes, so there were some difficult decisions. I hope people are, well, not too mad, but it happens. And we had 4 rejections, so they were not considered for anything. And because, well, I just said that the opening address is also the closing address, so at the closing address you thank people. So this big event, so we thank the student volunteers that we have here in the room, the POPL and the SIGPlan event organizers who are managing the whole thing that you see in the main room, and really they're doing really a lot of the logistics stuff. The steering committee, I was actually not aware who was on the steering committee until they invited me to be the PC chair. So apparently this is the steering committee, okay? I didn't know that. So it's Matthew Amy, Rose Duncan, Robert Rand, and Mathis Renel. I thank especially Robert Rand, because I was communicating with him a lot to set this up. The PC, of course, for reading a lot of papers or extended abstracts, and especially Jennifer Paking, who was acting as a substitute chair. And also thanks to all the authors and also the attendees for coming here. Okay, well, that's it, but just for the closing address that's supposed to be at the end, for which we don't have time. All right, now we move 9:10. We're exactly on time for the first talk. So, can the first speaker come? Perfect. Okay.
Was working.
Okay, that's good.
Okay.
Okay, so for the first contributed talk of the workshop, we have Jam Kabir Ali Khan. He's going to talk about estimating quantum proof classical programs.
All right, cool. Hello, everyone. Good morning. So I'm Jam. So I'm Jam, and this is joint work in collaboration with Anirudh Paduri, Gilles Bars, who is in the audience, and Michael Walter. So I'll be presenting track estimating quantum cost of classical programs. So we all know that many quantum algorithms do have advantage over the classical ones, and some example would be Grover's and the Shor's. And actually there is a long list of algorithms being tracked upon in the website called Quantum Algorithm Zoo, if you want to look it up. But then the question is, how do we leverage these existing how do we leverage these speedups in existing classical programs, right? We already have a lot of classical programs. How do we show that, okay, maybe at few part we can get that advantage from some of the quantum algorithms? So one of the ways to do so is quantization. And in this context, quantization could be kind of seen through this diagram. I'll explain. So let's say we have a classical program with subroutines, and these subroutines are performing some computational task. It could be searching, for example. And we apply quantization on this classical program with subroutines, and it transforms into a quantum program. And this quantum program and the original classical program are doing basically the same thing up to an extent. But then what do we how do we exactly concretely achieve this quantization? One of the ways to do is compilation. So you compile the original source classical program into a quantum program, and you get a resulting quantum program that does the same thing, but with a better algorithm that gives you some level of speed up. Okay, but then the question is, how do we estimate the advantage, right? Okay, we have a resulting quantum program that does this computational task with a different algorithm, but it's still, how do we know that this one is better than what we had originally? There are multiple ways to do so. We can execute it. We have the resulting quantum program. We can go run it on a quantum computer. But then, of course, quantum computers are not widely available yet, and it also tends to be more expensive. We can simulate, of course, and the simulation is also costly. It does not scale after a certain number of qubits. We can do manual analysis. A lot of people do this. They do this theoretical analysis of the cost. And of course, you have to do a lot of bookkeeping. Then it easily becomes tedious and error prone. So we are trying to find a fine balance between these approaches. We are trying to see if we can get something better. So in this work, the research goal is that we want a formal and practical framework to automatically estimate the quantum cost of classical programs. In summary, basically, we want to see how do we automate while maintaining some of the formal guarantees, this process. It has to be automated, as I said, so no manual cost analysis, no manual bookkeeping, ideally. It has to have formal guarantees, and also it has to be accessible to few people. So if you are a classical programmer, you just want to see if you can benefit from a quantum algorithm, you don't need to go learn all the quantum computing to do so. So let's see how do we do this. In this work, I will present track, which is the framework to do so. The way we do it is we introduce a classical probabilistic source language called CPL. We enable quantization that I mentioned before via compilation, and the compilation goes to an actual quantum programming language. And then based upon this compilation, we extract sort of a cost model. So there's multiple cost functions in this cost model, And we do this to kind of like estimate the cost at the source level. So you don't really need compilation once you have this and it's on. And of course, we give provable guarantees both for compilation and cost, as we'll see. So let's look at a simple example to demonstrate this process. So let's say it's a very basic example. We have a list, and we just want to find if there's a 1 or not. On the left-hand side, you have the program, which just simply performs mainly a search. And the search in this language is a primitive. So intuitively, we know that search is search, right? It could be implemented either classically with a linear search, or it could be very well a Grover's algorithm in the back. So track, the basic idea would be that the search primitive could have a classical compilation, but also a quantum compilation. The quantum compilation will go to a Grover's algorithm, and then you will have ideally a resulting quadratic speedup over the similar classical search. But there's more problems to it, as you will see. Let's take the previous example, make it a bit more interesting. Instead of a row, we are just searching over a matrix. In this matrix, we try to find a row with all ones. And here, what you will see is that now we have a nested search going on. We not only search on the outer rows, but we also search within the row to see if they are all ones or not. So as I mentioned, the search in this case would go to Grover's algorithm. Well, Grover's algorithm has certain constraints, right? The predicate should be unitary. Predicate in this case is this is_row_ones function. What it means is now we have to define a unitary compilation for the language as well. What it means to be unitary in the most basic sense is the resulting oracle or the program should be reversible. There's a more mathematical definition, but without getting into much detail, that's the most basic sense. So track does this. Track not only defines the general quantum compilation, but also takes care of this compilation which is unitary, so that the programs that you end up with are reversible. But then still the story of compilation is not over. There's more interesting problem as well of taking care of the errors. Most of the times when you write the classical algorithm, we don't need to worry about the fact that they can fail. Sometimes you will get a result that does not make sense, but well, quantum algorithms do. They have a failure probability. So how do we take care of this to make sure the resulting quantum program has a certain error, and it's not just errors that you don't know about. You have chosen the resulting quantum program to have a maximum error. So the way we do this, we take the source level code, we perform automated error annotation, because as I said, primitives are the one being compiled to a quantum algorithm, so the source of errors tend to be the primitives themselves, right? We annotate with epsilon1, epsilon2 in this case, for example. We run an error analysis. This error analysis is going to give you a expression which could be treated as a constraint, sort of. This error equation could be sent to a solver, or you could have some basic strategies to get the epsilon1 and epsilon2 values that satisfy this constraint. Once you have this, you can perform the compilation. Now the best part about this is that once you have solved this, you kind of know what the resulting program, how much error it's going to have, and you will get those guarantees. Okay, so this is the error analysis. So this is the compilation story in a sense, but then we also want to make sure that this is correct, right? What we are doing is correct, and we have to define the compiler correctness. And in this case, we do. I'm just going to show the general quantum compiler correctness in this case. So what we do is we give semantics to both the source and target, and reason about the distance, the TV distance between the resulting distributions from the semantics. Why we will do so is because the semantics for both languages are probabilistic, and we show that the semantics of both the source and the target are gonna be error close. So the error that you were comfortable with having in your program, that's the utmost deviation that these two semantics are gonna have. This is the notion of compiler correctness in our case. And then we also have unitary compiler correctness, because I mentioned there is unitary compilation as well. That would be in the full paper, not in this talk. But then, as I said, the original idea was allowing estimation of quantum cost, right? I have defined the compilation, but going back to the cost analysis, how do we do this? Before I get into the exact cost analysis, let's make sure we are on the same page about the model, the cost model that we choose. In this case, we choose query model, which is in the basic sense just counting the number of queries made to a function f. Why do we use this? It's sort of a well-established proxy for a lot of other models, time complexity being one. Also widely used in theoretical quantum computing literature. So precisely when we say a classical query is just a call to a function f. Inner setting, a quantum query is actually invoking a unitary UF, or its inverse. And exactly what it means to be UF in this case, it's defined by this statement. Okay, so now we know the cost model. What are the cost functions that we can get out of it? In this work, we have three. We have the havoc cost, input dependent cost, and unitary cost. The first two I will get into more details. So havoc cost. What does it mean to have havoc cost? Essentially, when we say about it's a sort of a worst case cost in the presence of errors. So what does it mean? So usually when we have a notion of worst case cost, we say, okay, our program is doing what it was supposed to, and here's the worst case cost. But in this case, there's errors, right? And those failure probability of the algorithm, it could do something that you cannot easily reason about. But it is still program execution. So not only we are taking into account the intended behavior, but also the chances that this program fails, and given all that, what is the worst case cost? That would be havoc cost. So let's look at how it works. We have the left-hand side, we have the program, and based on the structure of the program, we apply a cost function. And the cost function is just a havoc queue, and it's going to run and give you a cost expression. Some of the details are hidden because of complexity, but that's the notion of idea. That's the idea. Okay. Then we also support input-dependent expected cost analysis, and the motivation in this case is that we want to estimate the advantage given a specific input. Why do we do this? It's because a lot of these quantum algorithms tend to have a better expected cost over their worst case cost. So in this case of root n over k for growers, if you know the number of solutions, which is k, which is better than the worst case, which is just over root n. Similar to havoc cost, this also works structurally on the syntax of the program. And you run the cost function and you will get a cost equation. Again, some of the details are hidden for this talk. Yeah, so this is expected cost. And now let's look at the overview. There's a lot of equations going on. Let's look at the big picture of this whole theoretical setting, right? We define a probabilistic classical language. We gave it a compilation to a quantum language. We have the compiler correctness for it. Based on that compilation, we define some cost functions. Now you will see in the full paper, we have the cost correctness as well. The cost functions I just showed you, they are sound. Best part is once you know that this is all sound, you don't really need compilation, right? Your cost function could just run on the source level. And I think so this is the essence of this framework, that you can kind of take that quantum cost analysis where you need to worry about the quantum stuff, you can just bring it to the classical setting at the source level. Okay, there's a few more interesting things that we do. We have track implemented as a Haskell package. So the total implementation brings up to 9,000 lines of code, and we do some interesting choices in the architecture, one of them being that the AST is polymorphic over the set of primitives. What does it mean is that if you want to add a new primitive, you don't need to go changing the AST, which will lead itself to an expression problem, going through the whole 9,000 lines of code, changing everything. You just need to implement a primitive and pass it to the original AST, and you will get a new primitive. So it's, in a sense, it is more extensible because of this. And then another feature that we use for Haskell is we enable adding new primitives via type classes. So as I said, again, to add new primitive, you don't need to change the original structure of the code. There's a bunch of type classes. In this case, for example, one type class would be expected cost. You introduce a syntax, you implement those type classes, and the primitive gets added. Basically, if you want to support more quantum algorithms, this is one way to do so. So what are the primitives we support so far? We have the annual search. Some of these we already seen. We have the amplitude amplification as well. And we have the Simon's algorithm, which is very useful for cryptanalysis attacks. And we have min, max, argument, argmax. So these are the primitives that we support as of now. But of course, there can be more that could be added. Some of the case studies we do to show the applications of track are related to cryptanalysis. The most interesting ones being two is the 3-round Feistel attack and Ibn Mansur. So yes, so these are the cryptanalysis case studies we do. These are taken from literature. Then we have optimization as well. We have the max case set and we have 0-1 knapsack. So without getting details, the best part is this is existing in the current literature, right? We're taking problems from the papers that have already published. So we are trying to capture that in our framework to an extent. Okay, then to conclude, the list of contributions in this project include a classical probabilistic source language to express these programs. And then you have a compilation from this probabilistic source to a quantum language. As I mentioned, there's a few challenges we address to do so. Then based upon that, we have a cost analysis for the source programs to estimate quantum advantage. So basically, as I said, you don't need to compile. If this is sound, you can use this cost analysis at the source level, which is just write a classical program, get an idea whether it's going to benefit you or not to use a quantum algorithm. And then this all has to be guaranteed, right? This has to be correct. So we have the formal guarantees and a lot of theorems proved to do so on compilation and cost both. And as I mentioned before, we use some level of error analysis introduced. So those guarantees are based upon this error analysis. And then we have a Haskell package. The future directions for this work would include supporting more ghost models, right? The query model is good enough for certain purposes. Actually, it's a very good target for the start of the work. But then we might want to introduce gate complexity so we can get a better idea of how the hardware implementation works. And we can also enable support for more efficient quantum algorithms. There's, for example, a class of quantum algorithms called variable time quantum algorithms, and that would allow even better advantages for some cases. Yes, so this is the QR code to the archive and the QR code to the GitHub, and that's all talk. Thanks to you all for listening.
Would be the hardest to implement into the system. Like you can imagine if your classical program does some really weird control flow or memory or I/O, that might be pretty hard to compile to a unitary.
Yes, indeed, this is the case. So this leads itself to quite a couple of challenges that would not be addressed as the current work, right? So for example, I/O. We have not explored exactly how this would work out, but for example, we did explore adding, for example, boundary recursion or things to the source level language. So as a unitary compilation requires some level of constraints. We have to kind of deal with those and live within those constraints, right? For boundary recursion, we enable and a few extensions, for example, lists in the main syntax of the, so the full paper, if you look it up, it has more features including lists and some basic conditionals and boundary recursion as well in the code. But to add more features that are more complicated control for it will require some more exploration. I don't really have a better idea at that point. Yeah.
Thank you. With respect to the primitives, Grove and search, that gives you quadratic speed up on a quantum computer. Do you have, I missed that, do you have anything that also makes it possible to express quantum Fourier transform? Most programs that have any speed up, exponential speed up at all, seem to factor through quantum Fourier transform. So do you generate any of those programs?
So this is one of the interesting work we were looking into. So for example, having a primitive like Shor's or a quantum Fourier transform would be an interesting thing. For this, so far, we have added these primitives as of now. The interesting one being the general amplitude amplification and the Simons, and of course the search is kind of part of it. But yes, that would be definitely an interesting direction to explore, because that requires some level of changes in not only the compiler, that one needs to be careful of how they work out with the other primitives, the existing ones. So that's kind of an interesting problem.
Thank you for the talk. How about compositionality? Namely, for instance, if I have a search function that itself uses a search function.
All right, that is my first example indeed. Maybe it's going to be a long way. Okay, there we go. So this is actually quite an interesting case, right? This search is using a predicate that itself uses search, in a sense. This all is kind of a search. It's just the semantics are going to be different. But they are still using the underlying is Grover's algorithm. The compositionality is indeed crucial, so we do make sure that their theorems are compositional in the sense that as long as your primitives satisfy a promise, and you are kind of taking care of the constraints that are required for the compilation, this all theorems kind of compose. So we have a notion of functional spec. And in the case of the implementation, we also take care of type classes. So you just need to add it, and it kind of works into the system already. But in the theory, there's the notion of functional spec to prove those theorems instead of just relying on one specific primitive at a time.
Very cool, thanks.
Okay, thank you.
Okay, so let's thank the speaker again.
Oh wait, I took, yeah.
Okay, so our next speaker is Charles Yuan, and he's going to talk about programming abstractions for quantum linear algebra.
Great. Hi, everyone. I'm Charles. I'm from UW-Madison, and I'm really excited today to tell you about the work that we've been doing on linear algebra. So the setting of today's work is going to be talking about quantum computational linear algebra, by which I mean the ability of a quantum computer to deliver us all of these awesome advantages in domains that require solving linear systems, physical simulations, regression, differential equations, these kinds of linear algebraic tasks. Now, quantum algorithms are now known to solve a lot of these things very efficiently. What I think is really cool is that it actually goes even beyond those obviously linear algebraic applications. Much of our modern understanding of how quantum algorithms works is through linear algebra. Some of these cases are obvious. The HHL algorithm literally takes a matrix and inverts it. Some are a little bit more subtle. For example, simulation is all about taking a Hamiltonian A and computing its time evolution operator e to the minus iat. And even more surprising places, for example, Martin et al. Show in their great paper on the grand unification of quantum algorithms that even things like Grover's algorithm for database search can be conceived of as a linear algebraic task. In this case, you're actually going to be taking a sign function of a matrix, which you can kind of think about as discriminating the cases that you are and are not looking for. Now, the thing that these quantum algorithms give us is, in appropriate settings, up to an exponential speedup over their classical equivalents. For example, the HHL algorithm here can solve a linear system, invert a matrix of dimension n by n, in time that is polylogarithmic in the dimension n, as compared to the best known classical algorithms, which take time polynomial in n. All right, so this is that exponential speedup. Now, why should quantum computers be so good at linear algebra? Well, it's because in some sense they are linear algebra, right? We all know that qubits, their underlying mathematical representation is as vectors of complex numbers. And correspondingly, our operations on qubits are unitary matrices that multiply on these vectors, right? So that's the basic intuition here. I want to get a little bit more into the story about these polylogarithmic complexities here. Because if you think about it, it's a little bit weird that you ought to be able to invert a matrix in less time than it takes to just iterate over all of the rows of that matrix. There's something very suspicious going on. And the answer is, of course, that a quantum algorithm will assume a different access model to your matrix, some kind of sparse or structured access to that matrix. And indeed, over the last decade or two, the theory community has been working really hard to understand when this is possible and when this is not possible. So for example, in 2019, there was this really powerful theorem by Yuan Tang that showed that quantum algorithms that assume efficient access to arbitrary dense matrices can be dequantized into classical ones. So we don't expect that quantum speedup to actually be robust. On the other hand, in that same year, Gillian, Lowe, and other authors showed that for a big class of matrices that are comprised of these structured matrices like circulants, sparse matrices that only have a few entries per row, as well as combinations of these via algebraic operators, you are able to encode these efficiently into a quantum algorithm, and we're more confident that the quantum speedup will be robust. So this takes us then to the core problem that we have today. Here's an oversimplified illustrative example of how we're going to try to implement a quantum algorithm. Here, which is telling us that we're just going to take a matrix and invert it. What the algorithm will do, if you look at the paper, and again, this is oversimplified, but it'll take some sort of algebraic decomposition of that function of the matrix. Here it might look like this one. And then in turn, for all of these input matrices A, you're going to have to think about how to actually decompose that input into smaller matrices that could be individual unitary gates or smaller circuits that are provided to you as a black box circuit. All right? And then once you've done with that, you're going to need to actually turn it all the way into a quantum circuit program that can actually execute on the computer. So the claim that I'll make is this is actually a programming challenge. Right? The first problem that we're going to tackle today is solving this abstraction gap of going from an abstract mathematical representation of the matrices and the functions you want to compute in your algorithm to the actual circuit. And the claim that I will make is that you could use existing quantum programming languages to do this. You could take a language like Qiskit and use it to implement the individual logic gates that you would get out of reading these theory papers. But instead, maybe there's a better way. We developed a system in which you can actually just take the math, write it directly in terms of operators, here they're embedded in Python, and compile them automatically to this circuit. Now, setting aside the abstraction itself, there's also the question of efficiency. Given a circuit that we've produced, is there a way to shrink the number of qubits and logic gates as much as possible? Okay. The claim that I'll make here is that you could, once again, use off-the-shelf existing quantum circuit optimizers for generic circuits for this task, and you'll get a speed up of around 30% for these circuits. But again, maybe there's a better way. We can exploit the structure of these high-level programs that we're discovering here to get something that is closer to a 95% speed up. All right. So let me tell you about how we're doing this with a little bit more background. All right. So some definitions about how this linear algebra works. How does a quantum computer actually store and process these vectors and matrices? We just saw that qubits are vectors. Now, in general, we're going to want more interesting vectors than these two complex numbers. And for that, we're going to need a definition called amplitude encoding. All this is basically saying is that if I have an arbitrary vector in Rn, I can create a quantum state where the entries of that vector become the scaled amplitudes of this quantum state. All right. So this is the specification for how we take a vector and shove it into a bunch of qubits. What's the circuit implementation of this? Well, that's a more complicated story, okay? This task is usually called quantum state preparation in the literature. You can go to Google Scholar and find millions of results about how to do this for specific domains. It's still a pretty complicated open problem for a lot of vectors out there, but the good news is that this talk is going to work with pretty much any existing method for state preparation that you want, and so we're going to mostly set this question aside. The next question is about the matrices, right? Our unitary operators are matrices. How do we make it express all of the matrices that we would want in an algorithm? For that, we're going to use a theoretical construction called a block encoding. So here we're going to assume that we have an arbitrary matrix A, which is an R of n by n. And what we're going to do is embed it into the upper left block of a unitary matrix that I'm going to represent as B of A. All right, so what's going on here? The thing is that for an arbitrary matrix, it may not be unitary. Right? If it's not unitary, I have no obvious way of just writing down logic gates whose semantics equals that matrix. But we can still shove it into a corner of a matrix that is going to be unitary. That is possible as long as we take the original matrix A and rescale it by a factor alpha, which is called a subnormalization. That alpha needs to be big enough such that this upper left block is small enough such that the overall matrix is unitary. And in this notation, the dots are the other three blocks of the matrix, which can be arbitrary in principle, as long as this whole thing is unitary. Now, why do I want this block encoding? It's because it actually lets me do matrix vector multiplication. If I take a block encoding of A and I multiply it by a vector x, that's my input, along with some ancilla qubits, I get out this superposition, which has one of its branches equal to AX, the matrix vector product that I care about. There's also some chance that I get this bottom state. That's a failure state that I do not want. I can tell that it's failed because the ancilla qubits will not have been reset all to 0 on that branch. So in order to get the state that I do want, I need to perform post-selection. I repeat this whole process. I measure the ancilla qubits. I accept only when all my ancillas are equal to 0. How many iterations does that take? Well, that's of course proportional to something along the lines of that amplitude right there. Using oblivious amplitude amplification, I can do this in time O of alpha. The runtime of the program that enables me to produce the matrix of A is proportional to the value of this subnormalization. It's not just a mathematical trick. All right, so the good news is, from the theory literature, we have a lot of ways of actually taking our basic block encodings and combining them into interesting matrices we'll use in our algorithms. If you look at our full paper, we give you the actual circuit semantics for how to do this. I mean, I won't explain it in detail, but yeah, there are interesting ways of sequencing and parallelizing these circuits to give you all of these algebraic combinations. What I want to do instead is to skip ahead to an example. Here is a linear algebraic program that you might plausibly see in a quantum algorithm for simulation, where you've got like two particles and are trying to figure out how they're interacting with each other. So given this program, which will be the high-level input, our system, which is called POPL', will automatically synthesize this circuit for it. If you stare at the circuit a little bit, you'll kind of get the idea of where the structure is coming from. You know, we've got our kind of tensor product here along the two particles. We've got this addition and subtraction, and as well as this big addition over the top. This is kind of recursive structure here going on. Now, one question we'd like to answer about this program is, how much does it actually cost at runtime? So there are two main factors here, the number of logic gates that we're going to execute in the circuit, and something else that we'll actually see shortly. So that first part, right, the number of gates in this circuit. We can build this recursive cost analysis of it that basically just says, okay, well, if I'm taking the linear combination of two matrices, then that's going to require all the gates I need to implement the first one, all the gates I need to implement the second one, plus some additional overhead. All right. Now this overhead term just accounts for some extra gates that we're going to have around in that circuit. It's an implementation detail for the most part. We don't want to spend that much time thinking about it. And so one convenient thing we can do is, just like in the last talk, we can switch to a simpler cost model that only asks for the number of queries to the individual matrices in this system. So for example, here we really only care about the number of copies of x and y in the circuit. And the query cost in this case is just going to be the sum of the query costs of the individual matrices, and we'll not worry too much about that O of 1 term for this simplified analysis. Now, like I said, there is another component that we need to care about, which is the subnormalization. Subnormalization tells us the number of repetitions of the circuit that we need to perform in order for the final post-selection to be successful. And the theory literature, once again, actually tells us how to compute these subnormalizations. For example, the rule for a linear combination is that the subnormalization for the linear combination is the linear combination of the components with these lambdas, these coefficients here, absolute valued. That's kind of important, actually, to take their absolute value. OK, so as I just said, what subnormalization is doing is it's saying, well, for the actual computation, we need to repeat this circuit over and over again. Each instance of that circuit is going to take some number of queries. And so the total cost of the algorithm is going to be the product of the number of queries per circuit and the subnormalization, which is the number of copies of the circuit. We can compute the number of queries and the subnormalization basically recursively over the program. In this case, you can derive for that program that it takes 2.6 repetitions on expectation before your post-selection succeeds. All right, how do we reduce these costs and make the program more efficient? Here is a very simple technique that takes our example program and makes it more efficient. It's called sum fusion, and it essentially is just algebraically rewriting the program, combining like terms and all of that, so you get this simpler program. Right? Why is this program actually simpler and better at runtime? Well, it's because it corresponds to this shorter circuit. Right? There's only one addition going on. It is actually shorter. And not only is that the case, but also the subnormalization is smaller. I won't show that explicitly, but you can take these programs, do the computation here, and you can reduce the original big circuit, which is the total cost of 20.8, to this new circuit that has only cost 8. That's a pretty good improvement. All right. But I also want to talk a little bit about the limitations of that simple rewriting strategy. What if we have a more complex linear algebraic program, this one that I showed from the beginning of the talk? Okay, this is the circuit that it naively compiles to. Okay, it's got all of these A's and B's, and it's kind of sequencing them, multiplying them, doing all of that sort of stuff. We can once again just combine like terms. Right? If we do that, we get this algebraic simplification. It certainly looks a lot shorter, right? And you might hope that this will directly compile to a shorter circuit as well. But here is a little bit of a question that I want to ask you. And this is just in a classical linear algebraic setting. if I want to compute something like the product of A plus B with itself, where A plus B are both matrices, how many matrix additions do we need to do this? That's a bit of a quiz question. The answer is that you should only need to do one, right? You take A plus B, and then that's like a saved value, and you just multiply that by itself. One addition, one multiplication. All right, and similarly, what if I wanted to take a matrix A to the 128th power? What's the fewest number of multiplications that I need? I'll give you the answer, it's 7. You do exponentiation by squaring, right? A squared, A to the 4th, etc. You do that 7 times, you get A to the 128, right? And classical linear algebraic frameworks like PyTorch or whatever are basically going to use that trick of reusing like terms. But does that work in the quantum setting? Well, no, it doesn't. Okay, and if you have something like this, and you actually compile it to a circuit, you still wind up with a very long and complicated circuit. The reason is because for these block encodings of matrices, every instance of the matrix has to actually be represented as a gate in the circuit. You can't just say, well, I already have the matrix, I'm going to reuse it. That doesn't really make sense in this model. So even though the expression is shorter, the circuit is still long. We're going to need to do something more sophisticated, which is something that we call polynomial fusion. We're going to exploit the fact that not only are we just multiplying and adding matrices, it's actually computing a polynomial over the same base. We'll collect all of the coefficients into a list, and with this list, we will feed it into a theoretical construction called the quantum singular value transformation. Now, I do not have the 60 minutes that is necessary to explain the QSVT to you, but it's this operation that lets us get an efficient circuit that corresponds to a polynomial of a given matrix. There are some technical things that we need to do to make this work. Specifically, our contributions in this work include a type system that lets us check the hermiticity of the matrix to make sure the QSVT is applicable, to scale the coefficients of the polynomial, check its parity, invoke existing solvers like PyQSP to generate the phase angles in the circuit, and then produce the final output circuit. All the details are in our full preprint, but the bottom line is, when we do this, we can get a vastly more efficient circuit for these matrix polynomials that are more efficient not only in the number of queries to our matrices, but most importantly in the subnormalization. QSVT generally gives a much better subnormalization than our direct additions and multiplications. So I barely have any time left. Let's fly through some of the details in the full preprint. One of the things that we do is give an explicit formal cost model for all of the programs in our language. So for every operator, we can actually formally compute the number of queries in the matrices, the subnormalization, the number of ancilla qubits that we're using. There's a surprisingly high amount of math going on here, but one of the most interesting aspects I want to point out is, as I said before, if you're going to compute polynomials by simply computing monomials and then adding and multiplying them together, the subnormalization that corresponds to is actually equal to the mathematical L1 norm of the polynomial. Whereas if you use QSVT, you're getting the L infinity norm of the polynomial. L infinity norms are no greater than L1 norms, and in an example like this one, can be significantly less. Essentially, you're getting a lot of sign cancellation behavior. Based on this cost model, you can actually start defining these optimizations. So for example, the sum fusion operation that I talked about earlier is just reassociating the way that you are summing these things up, right? Rather than taking two big sums over small matrices, we're just combining these coefficients together and doing fewer additions. Polynomial fusion is just recognizing patterns of sums of monomials and collecting all of those into lists so that we can pass it into the QSVT subroutine. This seems very simple. The reality is that the compiler actually requires a whole lot more inference rules to kind of make this whole mechanism work, but I won't talk too much about that. Instead, let's talk a little bit about how this thing performs in practice. We asked, for example, how good is our system at reducing the costs of matrix expressions that you would find in applications? So here we studied a couple of different applications from things like simulation, regression, things like this, and we show overall, I think, meaningful improvements on these applications. We also wanted to ask how good is this system at resource estimation of well-known quantum algorithms. So again, we implemented things like matrix inversion, Hamiltonian simulation, and we show in this case that QSVT is performing fairly well. What we're doing here is that we're generating some of the very first executable circuit implementations of these algorithms. And finally, okay, we've also done an evaluation here. We compiled everything to circuits, we evaluated against state-of-the-art circuit optimizers, and we're showing that we are tying or outperforming many of these existing tools. There are some nitty-gritty next steps that we can do here to kind of make the compiler better, but let's skip over that because I want to end this talk on the message of saying, I think we've got something really cool here in terms of what looks like a quantum version of eigen, something that lets you actually build linear algebra, program, and reason about it in an interesting way. I think that there's a potential here for a big stack of quantum linear algebra that takes these applications and make them more realistic, the way that things like NumPy, TVM, JAX actually work in classical computation. So if you'd like to talk more about how we can build this sort of infrastructure, please come ask questions. Thanks.
Thank you. So many of the applications in scientific computing already have, as you said, structured matrices, but also sparse matrices. But even then, it's something which goes from quadratic to linear. So what's the black magic? Like, how do you get all the way to, and also in the classical setting, there's so much optimization that's already been done by a lot of people with massive libraries taking advantage of the structure. So what is the extra thing? I still don't get what's the extra stuff that you get and how you're able to.
The extra stuff in quantum algorithms or the extra stuff in our system specifically?
The extra stuff in quantum algorithms, but also how you are leveraging it to, in practice, to get what seems like 65% more.
Yeah, both of those are very deep questions, and I'll try to answer them very quickly. In quantum algorithms, the thing that you get is the ability to not explicitly represent your matrices as arrays of floating point numbers that you iterate over and try to skip as many blank spots as possible to exploit sparsity, which is what is being done in those classical ways. And instead, you have things like the QSVT, where you are natively computing a function of a matrix by approximating the inverse function of a matrix as a polynomial, and then for every term in that polynomial, you insert a copy of that matrix. That's not like a very intuitive definition compared to anything that we do in classical linear algebra, but I have to say that is just the fundamental difference in the input and the processing model. In our system, a lot of what we're aiming to do is automate that, take the structure in these applications and make it possible to take our high-level programmatic descriptions and lower them automatically to circuits. I mean, you could say that most of programming languages is about taking this kind of theory knowledge, mechanizing it, and automating it. I'd love to talk with you more about, how we can make these insights surface more as well.
Thank you.
Verifying RUS that repeat until success, I suppose, programs without a queue.
Okay, so thank you for giving us this opportunity to speak here. So I'm going to talk about our project on verifying the RUS programs with auto queues, and it's a joint work with many people's list of layers. So RUS is a program that aims to implement some non-trivial unitary gates using basic gate sets, for instance, and use measurements to collapse to these unitary applications, and also think on the success. For instance, in this, for instance, here is the RS circuits, and when the measurement is taken in Z basis, and when measurement outcomes once, it successfully implements the gates minus X gates applied to the inputs content state. And the RS programs turn these circuits into a loop so that if the measurement outcome is zeros, then we fail. Then we repeat the circuits, rerun the circuit until we success. So, okay, and here are some more realistic examples taken from the literatures. And here are some three iOS circuits that implements their intended unitary operations. But okay, but 2 out of these 3 iOS circuits are incorrect. In some sense, there are signs. I don't know if it's a typos or they actually implemented the wrong circuit, and the bug is found by our collaborators. And why we care about this? Because we care about correctness, of course. And the iOS circuits and the programs looks very simple, but still we can make mistakes. And this kind of bugs may propagate in your compilation pipelines, and it will affect your claim of your content advantage. And for us, of course, is one of the representatives. Very simple, the simple case of content programs with measurements and the infinite loop. Yeah. So our goal is to verify the functional correctness of the iOS programs automatically and efficiently. And our frameworks to verify this kind of program we reformulate the verification of content program as these triples. And here, the precondition and the postcondition are state of content state. And the C is the program we are going to verify. And the verifications will reduce to the validity of these triples. And the valid triples means that when we execute these programs from the states, from our preconditions, then after executing, after the program terminates, we want to show the states will satisfy the post conditions. And in our automata frameworks, we are going to, so we encode the preconditions and the post conditions as a label synchronized tree automata. This is a tree automata model encoding the state of content state. You just viewed the content state as linear combinations of computational basis, and it can be viewed as a perfect binary trees, and the leaves are the amplitudes of the corresponding basis. And the C and the content programs is executes using we design some abstract automata transformations to capture the content operations. And with our algorithm to verify these triples is valid is to first we run the circuits with the automatas that represent the preconditions, and after executions, we test the language inclusions between 2 automatas. And a few words about this model. So this model was introduced last year in POPL'26. We use some colors labeled by, the transition are labeled by some colors, so it can be used to synchronize the subtrees between in these automatas. And the advantage of this tree automata is more succinctly, it can represent more interesting sets of content states more succinctly than the standard tree automata models. And the cost of content operation, the abstract transforms has lower complexities compared to the standard tree automatas. And how we verify the quantum programs with loops. So here is the 2 examples we see in the first page. So it implements, when measurement outcome is 1, it implements the minus gate. And to turn it into the iOS programs, we represent the iOS programs as imperative languages, like as a while loop programs. And we use automata to represent the binary trees with symbolic amplitudes, and we execute our list programs and to obtain these trees. And when we perform measurements, we take either 0 or either 1 subtrees of these trees, binary trees. And the small detail is that when we perform the measurements, we didn't normalize the leaf, the amplitudes, but we delayed the computations to the inclusion test. The inclusion test in our tool is modified to test out of the constant scalings. And to verify these programs, we need to verify the triples, these 3 triples. The first one essentially says that the loop invariance will cover all the reachable states from the preconditions. And the second triples shows that the invariance is inductive. And finally, we show that the outputs will satisfy our post conditions. Okay? And but it looks very easy, but when we try to verify the RS circuits, the SMT solver never terminates and they always time out. But the reason is that the RS is not linear, so we demount the SMT solvers to help us solve the equations, but the formulas is actually a mixture of quantifiers, nonlinear integers, arithmetic, and nonlinear real arithmetic series, which is undecidable. So to overcome this, to limit these overheads, so we say, okay, let's try to verify this against the basis. Yeah. So in other words, we are not going to verify all possible quantum states, but only the basis. So the spec will respectively become very concrete, and it's a finite set of quantum states. The automata size is very small, and when we execute our algorithms, and it takes less than a second to finish all the verification. But this verification doesn't detect any bug, unlike And the problem is that the RSS programs are not linear, so it's not enough to check the correctness against the basis. So our first theories about this is that we show some characterization of this kind of circuit, this kind of programs. So it basically says that it's not enough to verify the correctness with respect to the basis, but you only need to verify one more vectors, which is entangled vectors, quantum states. Then it's enough to verify the correctness of the whole iOS programs. So this theory tells us that the really strong enough spec should be taken. This should look like this. Here, the F is the part of the iOS circuit, but before the measurement. Okay, so that's our idea to solve that. But there's another subtleties. So the language recursions used in our automata framework doesn't really enough to ensure the functional correctness. So the simple example is here. So here are two triples, and they both value triples, and they doesn't distinguish the programs. You apply the X get to the first qubit. So to this qubit, here is 1 qubit distance, and the identity operations. So it means that we need to ensure the one-to-one correspondence between the input and the output. So we need stronger notions. So we need to actually show that the precondition starts with color rate, must end satisfying the post conditions with color rate, or something like this. And to remedy this, so we can do that with the LSTA, our virtual automata models. So the observation is that we use some colors to produce the quantum states as the trees, and we collect all the colors we use along the executions. So these colors is invariance under our abstract transformation of quantum operations. So because of these properties, so we can design the language inclusions, but with color consistency, we can actually check that. And this is inspired by our recent work in this purpose. But the algorithm is fundamentally very different because they are designed for different models. Okay, so with this kind of of inclusion algorithms, so we can now distinguish X and identities. So for instance, here, this triples is still valid because you apply the X gates, the 0 becomes 1, and the 1 becomes 0, and satisfy our post conditions, but the identity operations will not satisfy because the colors are inconsistent. So putting everything together, so now our triples, so against the preconditions and post conditions are represented, encoded as LSTAs, and and we try to verify the triples of these three specs. These three triples in the sense, in the semantic of the functional correct of the color consistency, and here is the result. So we can successfully detect the bug. I mean the bug in the papers, and within less than a second, and the memory usage is not much, and that's it. So it's quick. I just want to mention what else we can verify with AutoQs. So we can show some equivalence parameterized versions of the equivalence implemented between different implementations of the Berzina-Balianis or multi-tuple gates. And for global algorithms, we can show, for instance, one iteration of global algorithm indeed increase the amplitudes of the solutions, and some parameterizations of some loop implementation of loops, and some weakly measured versions of global algorithm, the correctness of weakly measured version of global algorithm, which is is a loop, is a program with unbounded loop, and also the RUS circuits, RUS programs we found, and some other parameterizations of correctness of the. I have to mention that here the parameterized is not a parameterized content program is I mean the parameterized is in the sense of we verify the programs against all possible sizes of the systems. It's parameterized by the size of the systems. So I'm finished here. So, but before that, let me advisement. So tomorrow in VMK there is also condensations and the rubbers, and has some paper here, and the Marcos also. And in POPL, of course, there are condensations, but except that, so our new model to support parameterized verifications is in the automata sessions, not a condensation, but please come to our talk. It will be presented by our collaborators. Thank you. I'm happy to take the questions.
Is this working? Yeah. So I was wondering, the input to this verifier, the programs you're inputting to this, are they circuits with post-selection operations, or are they actually circuits with unbounded loops in?
Circuit with post-selections.
So how would sort of the machinery you set up here compare to? So surely you could sort of also compute a density matrix version of the post-selection. Does this give you something extra over? Am I missing something that I would miss? Like, can you cope with more programs in this setting than? Maybe I'm missing something. But.
Sorry, I don't understand your questions.
So if your input is the thing on the left, can you not just compute it as a density matrix and check that it is what you expected it to be?
Can you say again? Sorry.
So I'll talk to you afterwards.
Okay, no problem. Thank you.
Thank you. Enough time.
Any other questions? No. Well, maybe I can ask a quick one.
Okay.
So can you go to the table? Oh, yes, sir. Can you go to the table where you showed the results? So.
Yes, here.
Yeah, so in the literature, basically, what is the normal number of gates, let's say, in a RUS circuit? Is this a representative sample here? Do you do well with the ones that have been described in the literature? I mean, I'm basically asking if this is scalable, essentially.
Okay, so I mean, here these two failed ones are the circuits. Yeah, I showed in the very first page, and but this circuit actually implements the correct the unitaries. Yeah. Okay.
Well, my question was more about the size of the circuits in the literature.
Yeah, the size of circuits. I mean, it's a 2-qubit circuit and consists of 43 gates. Yeah, it's small.
Yeah. Okay. Yeah. Thank you. So let's thank the speaker again and move over to the
talk to us about path sums.
Yes, I cannot manage to put the slides. Ça a marché il y a 5 minutes. Yeah, it used to work.
Yeah, it was like it was.
Maybe if I just try to switch that, sometimes it does something.
Do you have HDMI?
Yes, I do.
Can
I
you
do.
try just
Maybe.
yes.
Yeah, we made a test just at the beginning of the break, and it was working all right.
Yeah, it does work. It does work.
Okay. 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 Do you hear me? Does this work? Okay, so hello everyone, and thank you organizers for the invitation. So I'm Christophe from CA, and I'm working on the development of a tool that is called Kubrix, and that aims at offering the possibility to perform formal verification of quantum programs. So I'm basically introducing some recent developments in Kubrix in this talk. Basically, the idea is that the field of quantum program verification has emerged and lived for maybe the last 10 or 15 years in a quite dynamic way. And it appears that a major challenge now is to lower the difficulty of using the tools that are provided by this field. In particular, I do believe very strongly in the strength of the path-sum symbolic representation for this aim, and this is basically what I'm talking about today. And in addition, trying to show you some example of some recent developments in Kubrix using path-sums. So I start with this consideration of the very simple schematic view on the so-called hybrid model. So there, the user of a so-called quantum computing machine actually doesn't address directly something that is quantum, but talks to a classical computer. And he builds a code that is a classical code with a classical control flow and so on. But sometimes it has a specific computing instruction that he delegates to the quantum coprocessor. The thing that is interesting for me in this scheme is that the user never directly addresses the quantum machine. And in some privileged scenario of usage, when at the time of building the code, of making the implementation, the user doesn't have access to anything that is quantum. And so there is a particular difficulty for programming. So it is the eternal question on how to get some insurance about what I'm doing. Is it right? Does it make sense does it physically make sense? And is it an actual computation of the calculus that I'm targeting? So in addition to
this problem of having access to the quantum machine. If ever this guy had this access, then there would be in the act of verification and debugging a certain number of difficulties, of extra difficulties that are due to the nature of quantum computing. And it is quite an avenue, but we cannot rely on test assertion because of destructive measurement that would falsify the the end of the execution. Final test is also hard to think about because what we want to verify concretely about a quantum algorithm is a distribution of probability. And so if we want to test it, we have to launch a number of tests big enough to rebuild a statistical distribution so as to compare it with the distribution of probability that is targeted. And so the short-term strategy so far has been to use classical simulation. That makes sense as far as someday there will be a quantum computer existing, and this is able to make some calculus that are out of reach for the classical computation, and this is where the real game is going to start. So yes, and with, in addition, the fact that it's not clear whether at time of implementation the user can really access the target quantum machine. So we believe in static analysis and the development of formal methods. So there, basically, we can talk about an engine, a classical program, that is able to look at the object quantum program to analyze its structure, and from this inspection to infer the behavior of this program. Yes, this scheme. So, in the last decade or decade and a half, we have seen some efforts from a number of places in the world for the development of formal methods dedicated to the quantum case. Here I put, so this is a sequence of some selected publications in the field. I put many colors just to illustrate the fact that if we look here out of the major formal analysis method existing in the classical case, so type analysis, abstract interpretation, automata, proof, and so on, and it looks like the community has been exploring all of the main existing solutions in the classical case and trying to adapt it to the quantum case. And so, in every case, basically, we can say so, we end up with relevant proof of concepts. And especially when the formal verification of quantum programs is at stake, there are several propositions that proved able to implement, specify, and formally verify all the major standard literature from the quantum algorithm zoo, at least in the FTQC case. So I think about Groover, phase estimation, Shor, and so on. So the conclusion of this period is that basically quantum formal verification exists and it is able to do things. Now, maybe a major difficulty is that even in the classical case, using the formal verification is something that is costful, and in many cases it is completely dissuasive for the user to be. And so, yes, in the general case, when it is about quantum computing, yes, we have the implementation of the algorithm. It is formally verified, but it is at twice aside the actual implementation in any shape, a kind of side program that encodes the proof of the satisfaction of the specifications for this algorithm. And in the general case, this proof is big, it's larger than the code itself, and it requires a user or the developer to write this proof code. We need some extra expertise and dedicated expertise and a knowledge and maybe something affective also towards the activity of formal verification. And so yes, this can be a dissuasive point if we think about proposing the formal verification to, let's say, industrial users, so someone with a problem that comes from the real world, that never heard about formal verification, and who maybe doesn't really care about it. Okay, so this is the challenge. To start introducing the solution I'm thinking about, let's come back to the very beginning, to the algorithm that we think about implementing. So here is a screenshot of the phase estimation algorithm taken from the Nielsen-Schwang manual. First thing that I observed is that the procedure, the algorithm, includes as a full white part a big or quite big, consistent preamble of specifications. So there are some input parameters that are declared. Here it talks about the size of the register, about the oracles, and so on. And within the algorithm, the specification function of this input parameters are given. And in particular, it provides some specifications for the correctness of the program. So basically, a success condition for run of the algorithm and the probability to succeed at each try. What is an interesting thing coming from that is that when we are implementing such an algorithm, what we are writing is a function that is to be run on a classical computer that takes as input some values for the parameters of the algorithm, and that outputs a circuit. And the circuit itself is a computing object acting over quantum data. So there is a double level of computation, an algorithm, a function from inputs to circuits, and then a circuit computes over quantum data. One thing that I want to emphasize on here is the distinction between verifying a circuit and verifying a program. And a circuit being the output of a program and corresponding to one specific instance of the input parameter. So adequate validation or adequate verification when we are talking about a program should be the verification holding for any possible value of the input data. Now, when we come to the description of the procedure itself, so there is a kind of specific format of this description. It's quite light and it is double columned. So first we have some declarations for the instruction, the computing instruction to perform. So they are just declared here. And aside these commands, there are step by step description, a mathematical description of the state of the system along the performance of these operations, and a mathematical description of its evolution. So here it's taken from a book. So it's taken from a book. So do you want me to use the
No, maybe just remove your patch.
Yes. Okay. Yeah. Tell me if it. Okay. So yes, the command, the declaration of the instructions are accompanied by your description of the evolution of the state of the system. So here we are in a book, in something that is destined to a human reader. So the stake is just to facilitate the reading and the understanding of the algorithm. But we think about implementation and we think about verification, and so this can be also a reference for trying to find a format for writing our specification and for the verification that we are looking for. So consider this. The definitive goal for this seek of simplicity informal verification would be to be able to write the code in this kind of format, by just declaring or defining or putting the main computing instruction and accompanying it with direct description of the state of the system in a format that would resemble as much as possible the format that real people are used to read and to manipulate. So it means that we assume, or we take it for granted, that we will have to input in the program some ghost material, so some information talking not about the operations to perform, but about the semantics. So we accept this as a prerequisite. And then the objective is triple. First, to describe the state in a format that is close as much as possible to the real-life description of state, and just mimicking this vectorial form. Then the objective is also to limit the ghost ingredient that we are going to input in the program to these intermediate descriptions. And then, of course, the far goal is to have a fully automated verification of this kind of specification. Okay, so the generic strategy from here is to integrate this kind of assertions in the object language, and then we have to design a verification engine. So I follow on with still the same picture. So this pink thing is just a zoom in from this part of this picture, and so this focuses on the format of representation of the state in these specifications. And just we observe that there are some patterns in this description. So each time the state is described as a sum of the vectorial terms, and each of the term is maybe a phase parameter together with a function pointing to the computational basis. And so we have this sum, and then it is normalized by a constant factor. And so the path sum symbolic representation that I talked about, basically, strictly speaking, is a formalization of this invariance. And it starts from the observation that for any state of the computational basis, for any unitary to apply, applying this unitary to these states results in a vector with this generic shape. And this generic shape consists in, again, a phase factor that is function of the input and the index of the path or of the vector term that we are in. Output function, again, function of the input and of the path we are in. That is basically a vector of binary function pointing to the computational basis, and a simple integer parameter that rules at the same time the constant normalization term for the whole sum, and also the range, the number of passes that composes the sum. So basically, there are how many sum terms as the number of possible assignment of R different path variables that are binaries. So it's, yeah, there are 2 to the R. Okay, so we have this format. Then we are just abstracting everything talking about vectorial complex states. So we don't mind about the sigma, about the complex exponential, and we just care so far about the parameters to enter in the Python format. And so we are going to just manipulate these simple data types. And given this tuple, so an R, a pH, and a K, something green, something red, and something blue, we are able to analyze a circuit and to read its evolution. So just to exemplify, so the formalism interprets the elementary gates. In particular, so here is the Hadamard. The Hadamard supports the quantum superposition. So in the PASM, it adds it increments the range parameter, meaning that for every pass in the original pass, after the Hadamard, there are 2 different passes. So the same for the other elementary gates. Then there are functions interpreting compositions, either sequential or parallel, and we can indeed walks through a quantum circuit and derive directly, by applying this transformation, a passum corresponding to this circuit. So this is a ground for symbolic execution, but yes. But it's not enough in the general case, because this gate-to-gate passum analysis is not optimal. And basically, there are more passums, we can see it this way. There are more passums than unitary operators to analyze or to compute. And so maybe we don't end up with the best passum and the best representation of the state we expected. So here is a simple example. It's a X gate surrounded by 2 Hadamard. So it's equivalent to a Z gate that just apply a phase transformation of -1, and with the gate-to-gate passum analysis, because we meet 2 Hadamard gates, because an Hadamard gate adds an element in the range, increments the range, then we end up with two different pass variables, which means a sum of 4 different terms. And so to manage or to deal with this effect, this equivalence or this extra information in the passum formalism, it is provided, in addition, a rewriting theory. And here, I paste the main rule in this theory. So basically, I won't go into the details here, but basically, it is able to identify some patterns with destructive interference between the different passes, and to cancel out these passes that interfere destructively. And in particular, it enables, in the case that we saw, to come back to a simple passum and the one that we could intuitively expect. So, as a conclusion about passums, they are a compact, flexible, and intuitive symbolic execution format. There are also some good, interesting meta-theory results. The calculus is complete and confluent for Clifford, and it is still complete, while not confluent, when we take a universal fragment of the calculus. So the Z star here means the Clifford plus arbitrary Z rotation gates. It has known great successes in the case when circuits were at stake for the problems of verification of specification and verification of equivalence. But if we think about, using them for the verification of programs as opposed to circuits, so with arbitrary size registers in particular, then there are still some drawbacks in the formalism. And upon them, the format is quite restricting, which makes much sense when it is devoted to the treatment of circuits, but which is less relevant for programs. Then the formalism also provides no means to analyze the measure, nor the quantum control, and of course it is non-parameterized. So using the toolbox for program verification will require some updates. So basically, just lifting the gate-to-gate analysis from the instantiated to the parameterized case is quite straightforward. So since a program is a function from parameters to circuit, we can lift the passum analysis as functions from parameters to passums. But now the challenge or the difficulty comes when it's about the rewriting and simplification of passum writings. And here I distinguish between three different cases of affairs, 3 different kinds of rewriting of reasonings that we need for the analysis of programs. The first one is just about rewriting along the theory of the leaf types, the leaf data, the simple data types that are used into the passums. So here is an example of just an equality between 2 integer expressions. So we need to be provided some means for that. On the other extremity, at the highest level, we also need, by experience we saw, some means to reason in contexts where past sums are taken as basic objects and to make some reasoning about their composition. So here is the switch between the sequence of two parallel composition into the parallel composition of two sequences. So this is a second pattern, and the third one corresponds to the rewriting in the sense of the past-sum theories. It is when the very structure of the past-sum is involved, and when there are some transformations that affect at the same time the different components of the past-sum tuple. And this is basically harder to proceed. A little aparté on the formal verification technique that I'm using. So it's called deductive verification. Basically, we can write some object language code and explicitly annotate it with some precondition, postcondition, and loop invariants, and so on. And I'm working embedded into a tool that is called While3, and that has the particularity and the advantage that when we compile this decorated code, so it raises some proof obligations to discharge. And to discharge these proof obligations, we can directly address a number of SMT solvers that will try to make the proof completely automated. And as an alternative, yes, it's not in the slide, but as an alternative, While3 also provides an access to a user interface where the user can enter some commands for the simplification of proof obligations. So there are these two possibilities, either research automation or make the proof or input something to the proof to help the dischargement. So some demarcation criteria about that. Yes, it's quite intuitive. Basically, if the proof doesn't involve the introduction of extra parameters, then we have good chance to believe that they will be automatically discharged by the prover. And if we need to input some information to make the rewriting or the transformation, then it's more complicated. And so basically, it fits more or less the distinction that is there. And when it is a rewriting of a past-sum, generally it implies a factorization, and it needs to provide the proof a pattern. And when it is about algebraic reasoning about past-sums or rewriting simple data types, then we have better chance to have the proof completely automatized. And so the strategy here is to take the best profit on SMT solvers and to let them in charge of all the proofs about algebraic reasoning and internal types reasoning. And for the last category, the rewriting, to explicitly command the rewriting from the object language. And so this rewriting rule will be full write instructions from the object language. Okay, so basically, maybe I'm going to be quick on that, but this is about the updating of the rewriting theory to the parameterized case. So here is the generalization of the HH rule as an application to an arbitrary sized register. So I called it the QFT rule, and it's quite cool, but I think I don't have time for going further on it. Also, a generalization of a principle of substitution of variable that is present for circuit in the original theory as a substitution of one single variable, and then here it is updated as a substitution function for, again, an arbitrary sized register of path variable. In addition to that, the past-sum the past-sum also provide tools, or naturally inspire some tools for reasoning out of the pure unitary case. And concretely, there is a continuity between the representation of an operator and the state. Basically, a state is just a constant operator. And there are also some tools to reason on the deletion of information. So here we have the parallel pass-sum composition scheme, and it also has a variable precondition for the separation of a state over different registers, and enabling to define a discard operation about the object. We also have tools for formalizing the projection, so for the analysis of the quantum measurements. So basically, when a path sum ends up with the direct mention of some path variable in a given subregister, then we can fix these values for this register and delete the sum over the corresponding path variable. This enabled to treat the measurement result for the major FTQC algorithm that we meet in the literature. So far, I didn't meet any case where this projection scheme, together with the possibility to apply the variable register substitution, I didn't meet any case where it wasn't sufficient. Okay, so I end up with a quick show of the implementation experiments that I led recently. To do so, I just introduce a little bit of syntactic sugar. So here, the object, what we are programming, what we are building, is not just a circuit, but a couple of a circuit and its interpretation. So we have this couple of an instruction or a set of instructions and a PPS, that is a parameterized path sum. And basically, the kind of specified assertion that I use is this one, where there is an initial state, and then there is a variable configuration, so a variable object of this type. And the idea is that we apply some configuration updates, and this function here, that is a syntactic sugar, ensures the fact that the satisfaction is preserved along the update. So which basically mimics a OR assertion from the initial state. If my config is correct before, which means that the path sum represents the execution, or the execution ends up with the path sum, then it is also after my new instruction. And so we can use it as a primitive to implement the algorithms that we find in the literature. So here is, as an illustration, the CHOSA. So there is a preamble of declaration of parameters and the specifications of the algorithm, two consecutive definitions for the path sum intermediate state that we are going to meet, and then we can make or write the computation just by using this update specified assertions that we meet before. So here is the circuit, and we find the different instructions corresponding to the box that are represented. So we place an Hadamard gate, then there is a composition of a parallel composition of Hadamard, the oracle, and again a column of Hadamard. Another illustration, so I didn't introduce the circuit, so I don't know what it really holds, but this one is a bit different because it involves, in addition to some purely computing instruction, some rewriting instructions, and they are there. So here we have the circuit itself, and then two different rewriting instructions, one occurrence of a variable or variable register substitution, and one occurrence of the QFT rule. And so the format is homogeneous. And the third example is, because it is the one that we saw in the picture, it is the quantum phase estimation. So here again, a preamble containing the general specifications, a little bit of intermediary definitions, and in particular, the intermediate path sum description state definition, some definition for the instructions, and the core code formatted by this specified instruction function that I introduced. And there is also a post-process dealing with the analysis of the end state and deriving the specifications for the probabilities. Okay, this is the one. So as a conclusion, so if I come back to the code, to the goal, that was to make the code basically look like this as much as possible and to not require any extra input. I would say that I'm quite happy with this objective. First, about sticking to the vectorial nature format as far as possible. So here I think the PASM is very powerful because it is really, strictly speaking, it is just let's say, natural or the common or the standard or the literature format for the description of states minus some elements. So it is exactly that, minus the sigma, minus the complex exponential, and so on. About the objective to limit the ghost ingredient to this, so globally, it's not far from that. I didn't insist on it, but the delta towards it mainly consists in the fact that there are iterators that are provided by the language, and applying the iterators needs to input a PASM invariant. So this is the main delta. And about the objective of full automation, I would say I'm on the way to it, I hope so. So some of the algorithms or some of the experiments that I led could support full automation, like for the Fourier transform or the Dutch IOSA. And I have a residue for the phase estimation, for the modular addition that we saw quickly. Also, there are a residue of human command to enter to finish the proof. So this is a count of how many times I had to enter some extra information in the proof. Yes, basically that's it. And yeah, further direction would be to extend the practice and the formalism to the hybrid case. And also, I'd like to tackle the consideration of less structured cases than the one that I talked about. Thank you.
Any questions?
Thanks, and thank you for your talk. I'm curious. I think that this is just like a clarification question. So how do you capture like algorithms that involve measurement, for example, or even going beyond like into hybrid classical quantum classical algorithms? Are those sort of expressible in this system in a scalable way? I just didn't quite understand.
Yeah, thank you for the question. I don't have the definitive answer to this question. Okay, but actually there are two levels of partial answer. How do I handle the measurement? So far, basically, I have this kind of partial solution, and I've been a bit quick on that, but you know, when you have a PASM, if you have the luck that at the end of the analysis, in your PASM, you have directly the expression of direct path variables, then you can just instantiate them, and you have the projection of your original PASM to the state that you expect. So this is quite restrictive, but we can rewrite, if we find the bijection, we can rewrite the variable, so it opens a bit the preconditions, and maybe I had luck so far, or it happened that these cases, these pattern or this tool unable to formalize and to analyze all the standard algorithms that I found so far. So yes, there is a question anywhere about where does it come from, and is there something complete? Can we always find the bijection, and at which price? Do we have a heuristic for finding it? And so far, yes, my answer is that I didn't go further into this question so far, and yes, going over just the using of this scheme, is a part of extra or further projects, I would say.
Any other questions? Yes.
Thanks. On your last slide, you said one of the dreams was to handle less structured cases. What's the sort of structure you rely on at the moment? I didn't quite capture what this handling less structured cases means.
Are you asking me what I'm thinking about when mentioning less structured cases?
I'm asking what current structure you depend on, like what structure is being taken away in this sentence, I guess.
Sorry, again, I'm not sure to fully understand the question, but what is the advantage I take from structured cases so far? Or?
I'm asking what do the less structured cases look like?
Yes, I'm thinking of, basically, you know, I've been working with Groover, with QP, with the QFT, and where there are lots of gates, but there is one or two loops or one or two iterators and so on. And I'm basically thinking about how this formalism would behave in a circuit where each instruction would be different. And so I like to see what happens for VQE, for example, and also if it makes sense, maybe something that has been post-processed at some points, and yes, resulting from a step of compilation, and what can we do, and if everything is not structured and with beautiful generic transversal boxes, what happens?
Okay, thank you.
That's it.
Who will talk to us about ranks.
Okay, I wasn't expecting that. Yeah, you could say it's...
Okay, one rank to control them all. Is that what you expected?
Yes. Thank you for the introduction. The title is funny. I could give you a list of actual titles we had thought about. This is Chris's choice, so not my fault. But it's also not very informative, so I'm gonna have to work out the explanations during the talk. Well, All right. We're going to talk about quantum circuits. Quantum circuits have been around for a few decades now. And, well, I hope I'm not going to be rude, but I'm going to explain what quantum circuits are. So you just append gates. You have a bunch of things that you can put next to each other. And you can also have several wires. The reason why I'm saying this is that one thing I want to focus on is this. So the hidden thing in quantum circuits is the tensor product, and it's the one important thing that we don't see in the picture. And well, it's something that now everyone uses, but do we understand quantum circuits that well? Well, we'll see. Maybe you understand quantum circuits better after my talk. So the first complete equational theory for quantum circuits for all unitaries came out in 2022. I should have listed the authors, sorry. Well, this is very recent. We could have expected something earlier if we actually understood quantum circuits that well. And actually this result came out thanks to completeness for optical circuits. And now, the other interesting thing, and which we're going to focus on, is that optical circuits are also circuits, but the hidden thing between the wires is a direct sum and not a tensor product. This makes it a lot easier to manipulate. And then, through this result, they were able to come up with an equational theory for quantum circuits. But that means that the heart of the result is here, and not for quantum circuits, let's say, natively. So here it is. I actually cheated because in the first paper they don't have one equational theory, it's scattered. So to put on the slides, I chose another. These are pretty usual equations. So you have phases that you can sum, you have H gates that cancel. You have this triple C naught that makes a swap. This is, well, the Euler decomposition of the Hadamard gate. This is the general one. And then there is this mystical thing. It's necessary, but, well, now we have easier presentations for complete equational theory. But anyway, this is not really informative. What I'm going to try to get to by the end of the talk is why this is important, and I'm going to explain it through this, the diaxon. So in the original paper, the first paper for the complete equational theory, there is a distinction between structural equations and non-structural equations. And I'm going to quote the paper, because it's quite important. So these structural equations are structural in the sense that the transformations on the parameters are only based on the fact that R is an additive group. Did anyone understand that? Okay. In my case, I'm going to talk about structure in a slightly different way. I'm going to insist again on the direct sum. And in my sense, structural equations are equations that come up from the structure of the direct sum. And now, to see if you have a good, I don't know, intuition about these things, we're going to play a game. Okay, raise your hand if you think that this equation is structural. Okay, good. It is. So it is in the sense of the authors of the equational theory paper. It is also in my sense. Everyone happy? Okay. Raise your hand if you think this equation is structural. Okay. It is structural, according to the other authors. It is not in my case. But it doesn't really matter. Raise your hand if you think this equation is structural. Okay, it is. How about this one? It is as well. Okay. How about this one? Fewer and fewer people. Well, it is. How about this one? So now I need to explain a bit because this is not such a usual gate. V is the square root of x. So V squared is the NOT gate. Is this structural? Haha, it's not. So this is in the early decomposition, and it's pretty much, in my sense, the only equation that is not structural. Well, now I've spoiled you. And how about this one? This one is quite interesting, and it is in both sense. This equation is well, basically how you use fewer controls in your circuits. So control is expensive in a sense, and if you want fewer controls, you can have more T gates instead. Okay, and my notion of structure is about the direct sum, but it is mostly about control. What you see on the circuits is control. Okay, I'm going to scroll through this quickly. So if you want to describe a unitary, you can do it by only describing it on the basis, and so this unitary here, for example, C naught, you can describe it on the basis for 2 qubits, and you get this matrix. And the interesting thing to see here, but probably most people here are used to this, is that it is a block matrix. So here you have the identity, and here you have the NOT gates. And you can generalize this to all unitaries. So a controlled unitary is identity U. So, and this block matrix can be written as this. So identity O plus U. So the direct sum is hidden here when you write a control. And funnily enough, Z rotation gates are also of the same form. So you have the block identity and the block something. So you can write it as a control. And we're going to talk about all this mathematically. So we're going to do a bit of category theory, but in a very chill way. So a category is made up of objects and morphisms, and you can compose morphisms if they have the right type. And in our case, we're talking about circuits, so the objects is just the number of wires, and we call that a prop. And the number of wires can be summed, and in our case, if we talk about quantum circuits, the sum is actually interpreted as the tensor product. And if you talk about linear objects, it's the direct sum again. So there are several possibilities for the sum. And an important thing, and a very nice thing, is that a prop can be described by generators, and well, by generators and equations, like a group. Now I'm trying to make more sense of what is structural, give a proper definition of what kind of equations are structural. And based on this mathematical setting, I consider that structural should correspond to something that you can add, like literally a mathematical thing that you can add to your theory. And my point here is that control is going to be the answer. So the structure, the reason why some equations are structural is because they correspond to the addition of control to the theory. Okay, so start with any prop that you like. Well, not any. But let's say for circuits, so your generators are reversible, and you have a NOT gate, which is going to be important. Then for all morphisms in your category, you add its control, and its control of control, and its control of control. It is a very syntactic construction. For now, there's pretty much nothing about it. And then you quotient by all these equations. It is fairly easy to understand them. So the composition of control is the control of the composition. Control of the identity is the identity. Control behaves well with the tensor product. You can change the color of your control. So this control triggers on 1. This one triggers on 0. If you change the value, you change the color. If you have both colors, you trigger on 0 and on 1. So you basically just do the gate. If one triggers on 0 and the other triggers on 1, you can swap them. This thing, the swap. And also the control behaves well with the swap. Okay. A very recent paper by Simon Perdry and Noé Delorme came up with this equational theory for quantum circuits, which is much, much nicer than the one I presented in the introduction. And there is a line dividing structural equations and non-structural equations, kinda. And all this, as you can see, is about control, and is actually about, I forgot the word for it, conjugation. No? Anyway, you have two inverse gates surrounding another. And all this is about control, and I can show you that all those equations are derived from my theory. So if you have conjugation with control, I'm going to add in the middle, well, 0 controlled inverse of H and 0 controlled H. This one commutes over here. And since I have the inverse of H that triggers on 1 and on 0, it's just the inverse of H. And here I have H that triggers on 0 and on 1, so it's just H. So this is part of my equational theory. And now we can do this thing that we did syntactically, but mathematically. So again, if you start with a prop with a NOT gate and some generators, you build a completely new one. And now the generators have type 2 to the n, because we're not interested in the number of wires anymore. We're interested in the number of dimensions. And now this new prop will have a structure, not the tensor product, but the direct sum. So now when we append wires, we'll write it with a direct sum. And we can do some magic. So the identity from the prop you started with transfers to the identity. Composition is composition. And then we can also translate the tensor product in this new setting. It's a bit disgusting, but This is simply a Kronecker product. So you can write. So this is a block matrix with a bunch of H's, and with the right swaps, and you compose with the same block matrix, you obtain the tensor product that you can define only with direct sums. And for now, we've just used the generators from the category you started with, and we're going to quotient with this thing. So our definition of the tensor product here doesn't force it to commute. So if you have a gate on one wire and a gate on another wire, they can the order doesn't matter. So you need to transfer it. Well, you need to force it. And the NOT gate is also needs to be forced to be the swap in this new category. And by quotienting by this, you obtain a new prop, and the main result is that this is, if you focus on objects that are power of 2, so just on qubits, this is exactly the same category that the one we had syntactically. So adding a control theory is literally the same thing as working with direct sums. So control is direct sum, full stop. A few examples. There is a nice paper about quantum theory with Z2. And this is the two generators that you need. This is a funny matrix. And if you want to define the prop, you have two generators that are x and j. And x squared is the identity, j to the third is the identity. And then you have jxj, which is x. And to this prop, you can add control the way I showed you, so either syntactically or mathematically. And finally, this is not complete yet. By just adding control, you need to quotient by a last equation, this one. I could find this thanks to some very nice work from Yves Lafont. Otherwise, I couldn't make it. And you can do the same for quantum circuits then. So now you generate everything with phases, z rotations, and some h gates. And you define them. So this is what you can do at the 1 qubit level. You add control the way I showed you. And this is not complete yet. But if you quotient by this, it becomes complete. It's a bit funny. Okay. Right on time. So the one thing you need to remember is that control is exactly the direct sum. And in a sense that is very general. So all equations that are about control are exactly the mathematical interaction between the direct sum and the tensor product. So the fact that the tensor product distributes over the direct sum gives you all the equations around control. In category theory, this is called the rig structure, hence the title. And one of my points here is that if you want to design a programming language that manipulates these kind of things, maybe it would be better to have a type system with both tensor product and a direct sum to handle these matters. Or a nice way to introduce control, and Alex will talk to you about it later this week. Thank you.
Any questions?
So great talk. I really enjoyed it. I was wondering, so I'm now trying to go back to the examples that you gave and the things that you said were non-structural. And
do you want the? Oh yeah. This?
Yeah.
Okay.
So, firstly, can you walk through why HH is structural according to one interpretation and not the other now?
This is a great question. It's because of this, but I do not really understand it myself. But that's what's written in the paper, and they include the HH cancellation as structural because of this.
But it's not structural according to your definition because it can't be easily defined in terms of the direct sum?
Yeah.
Okay.
Thanks for the talk. My question is,
Thank you.
what's the relation of this to optical circuits? Because the reason that they use the direct sum in optical circuits is because there's this embedding of the unitaries on the complex numbers into the unitaries on L2 of R. So it's really like, in the representation you have the direct sum, which is like turned into the tensor product in infinite dimensional Hilbert spaces, so it's not a rig category. So is there some you can say about the optical circuits with your framework?
I'm not sure. Okay, wait. So the results, well, first, the complete equation of theory is just for finite dimensional optical circuits. You have, I'm not such an expert on optical circuits, so you have, I think, many ways of representing them. So this one, well, the one I was talking about is based on the love calculus. I'm not sure that works with your what you just said about L2. But I guess we'll have to chat about it more deeply.
So I'm sorry, we are already late. The organizer is going to beat me on the head. We allow one more question, so we have to thank the speaker again and delay the question. Space is revisited through Von-Neumann co-algebraic approach.
Thanks for the introduction. Wait, is it too loud?
Yes.
Okay, so as you might have guessed, I'm going to be talking about like categorical models of multiplicative additive linear logic. So you might have already heard of stuff that are called quantum coherent spaces, or kind of vaguely looks like what one would think of as quantum coherent spaces. So most notably, there's the approach by Girard. But I mean, this approach has been widely criticized because it doesn't properly capture quantum channels. Then there's also like the cost construction by Simonson and Kittinger, and also the work by Tsukada and Asada. Note that they don't claim to be quantum coherent spaces, but the methods are based on like, or inspired by gluing and orthogonality. So like their construction looks very coherent spacey. And while they can talk about complete positivity, they assume complete positivity on their base category. By comparison, in our approach, we don't assume complete positivity. It's only derived when necessary. For example, for mixed state computation, which also enables us to talk about pure state quantum computation, because we don't want complete positivity there. And also our formulas, or like our polarized formulas and the polarized linear logic duality have physical interpretations. So there's a concrete description of them based on mathematical physics. So before we get started, we should naturally ask ourselves, what should quantum coherent spaces be? So there are two views on what quantum operations or quantum channels are. There's the Heisenberg view, in which these are completely positive unitole maps, and then there's the Schrödinger view, in which these are completely positive trace-preserving maps. So we would like a model of classical MAL, where the proofs of formulas with positive logical polarities are CP-TP maps, and then the proofs of formulas with negative logical polarities are CPU maps. And then we want the polarized linear logic duality to coincide with the Heisenberg-Schrödinger duality. So it should take CPU maps to CP-TP maps and vice versa. So we're going to work kind of categorically here. So I'm going to organize the Heisenberg view and the Schrödinger view into two categories, and we're going to see how the Heisenberg-Schrödinger duality is described. So for the Heisenberg view, we have objects that are finite-dimensional Hilbert spaces and CPU maps between the spaces of bounded operators on these Hilbert spaces. And then for the Schrödinger view, we have finite-dimensional Hilbert spaces, again, as objects, but the morphisms are CP-TP maps between the spaces of trace class operators on these Hilbert spaces. So usually, the Heisenberg-Schrödinger duality is described as a set isomorphism between CP-TP maps in one direction, and then CPU maps in the opposite direction. And having organized stuff into categories, you can see that this gives us an equivalence of categories between the Schrödinger category and the Heisenberg category opt to account for the switch of direction here. So we wanted a model of MAL, one category that's a model of MAL. The problem here is that these two, they live in different categories. So we would like to organize everything into one category. And also we're kind of skewed towards the Heisenberg view because CPU maps are also morphisms between von Neumann algebras, which are more general than these B of H spaces. So what becomes of the CP-TP maps corresponding to these CPU maps between von Neumann algebras? What's a good notion of dual object for von Neumann algebras? Okay, this kind of naturally brings us to the theory of operator spaces, because all of the constructions that I mentioned before are things that make sense in operator space theory. So if you're not familiar with operator space theory, it's usually thought of as the non-commutative or quantized version of Banach space theory. So the constructions that we can do in operator space theory kind of parallels the ones in Banach space theory. And we know that Banach spaces are quite nice categorically. So it's not very far-fetched to assume that we could do similar stuff using operator spaces. And it's also worth noting that this is a very rich theory. There's a lot of interesting constructions already that we can make use of. So there's a lot of tensor products. For example, there's the Hall-group tensor, which is non-commutative and self-dual in a De Morgan sense, which is kind of rare. This holds only if the spaces are finite dimensional, which is what we're interested in anyway. So concretely, a finite dimensional operator space is a pair with an underlying finite dimensional complex vector space, and then a sequence of norms, one for each space given by the tensor of the underlying space, and then tensor with the space of n by n complex matrices. And this sequence of norm, of course, satisfies coherence condition that we're gonna sweep under the rug. So an example of an operator space is take the n by n space of n by n complex matrices, and then take the operator norm, like this as a sequence of norms. This is like the most simple example of like an operator space. If we take the dual space of this MN space, we get the space of trace class operators, and its ground norm is precisely like the trace norm. So okay, we have our objects. What about maps? So you know that a linear map between two vector spaces kind of induces a linear map between the codomain, the domain and the codomain, but tensored with the space of like n by m matrices. This is called like the nth amplification. So for operator spaces, the sequence of norms is what's important. So what the type of maps that we're interested in here are linear maps between operator spaces, such that each of the amplifications is a contraction. And this is what's called a complete contraction. And of course, like CPU maps and CPTP maps are complete contractions. So, okay, we've gone through a little bit of background. Now we can introduce our base category, which is the category of finite dimensional operator spaces. It has objects that, of course, are finite dimensional operator spaces. And then the morphisms are these complete contractions that I mentioned before. And it's denoted FDOS. And this category is very nice because it's a model of MAL. So it's star autonomous, and it has finite products and coproducts. And you can see in this table above how each of the like MAL connectives are interpreted in FDOS. And then note that these are quite natural constructions in operator space theory. So we're not like using categorical tricks to get something unnatural. So you might also notice that this connective here doesn't really belong. It's not a MAL connective. It's actually the set connective of BV logic, which is like kind of an extension of the multiplicative fragment. And it's a connective that's self-dual and non-commutative. So I mentioned before that we have a tensor that's self-dual and non-commutative for operator spaces. And in fact, we can kind of interpret the set connective using this tensor because this tensor, the Hagrave tensor, gets us another monoidal structure on FDOS. And together with the star autonomous structure that we have from the MAL structure, FDOS is a BV category with negation, which like for you who don't like category theory or like don't really care, this just means that the self-duality and like the non-commutativity is like quite nice. They work nicely with the like other multiplicative connectives. So, okay, we have a nice base category, but operator spaces do not have sufficient structure for quantum computation. So we wanted the Heisenberg-Schrödinger duality. So CPU maps, I said, were morphisms between VN algebras or von Neumann algebras. But for CPTP maps, what are they morphisms between? Like, okay, these are dual. We want something that's dual to a von Neumann algebra. But if you know how a von Neumann algebra is defined, you know that it's very like functional analysis. It refers to norms. It's not easy to dualize or like know what the correct notion of dual of that would be. So what we've done is to define von Neumann algebras categorically. And in category theory, it's very easy to dualize things because you just take like the opposite. And this categorical definition is of course completely equivalent to the regular definition. So now we can organize our Heisenberg view into a category where the objects are von Neumann algebras and the morphisms are CPU maps between the von Neumann algebras. And then for the Schrödinger view, we instead have von Neumann coalgebras. And the morphisms are CPTP maps. So the categorical definition of a von Neumann algebra is that it's a certain type of involutive monoid object in the monoidal category given by the Hagrave tensor on FDOS. And of course, there are coherence diagrams that I haven't shown you. But essentially, that's what it is. So now for the notion of positivity, we can give a categorical definition of positive elements in a von Neumann algebra. And then we have that a linear map between two von Neumann algebras is positive if it preserves positive elements. And then it's completely positive if each of the amplifications is positive. So a CPU map is then a CP map that preserves the unit of the monoid structure from above. Now, just completely dualizing what we had on the previous slide, we get that von Neumann coalgebra is a certain type of involutive comonoid object in the same category as before. Now for the notion, okay, also coherence diagrams, we just switched the arrows around. So for the notion of positivity, we just like dualize what we had before. So instead of positive elements, we get positive linear functionals on a von Neumann coalgebra and a linear map between two von Neumann coalgebras. So hard to say. Is positive if it reflects positive linear functionals, and it's completely positive if each of the co-amplifications is positive. So a CP-TP map is a CP map in the sense here that preserves the co-unit, because essentially co-unit is category theory talk for trace. So I mentioned that like the Heisenberg view and the like Schrödinger view are these like polarized fragments of linear logic, or they should correspond to that. And in fact, the category H here, the one that we're interested in of von Neumann algebras, is actually symmetric monoidal with respect to what we interpret the par to be in FDOS. And then it has finite products given by the width, which are, so the par and the width are the two negative connectives in linear logic. So this corresponds completely to like the negative fragments. And then for S, we have that it's symmetric monoidal with respect to the tensor, and it has finite co-products given by the plus, which are the two positive connectives. Okay, so I kind of said that von Neumann algebras and von Neumann coalgebras are dual to each other, kind of informally. But actually, this duality coincides with the operator space duality. So what I mean by this is that if we're given a von Neumann algebra, its operator space dual is canonically a von Neumann coalgebra, and also vice versa. And in fact, the operator space dual induces an equivalence of categories between the Schrödinger category and the like Heisenberg category opt. And this kind of recovers categorically the Heisenberg-Schrödinger duality. And also note that this equivalence is strong monoidal and co-product/product preserving depending on where you put the op. So we do have that the polarized like linear logic duality is the Heisenberg-Schrödinger duality. But okay, we have a model ML. We have two subcategories that corresponds to these like two pictures. They are polarized fragments. But the problem here is that these embeddings are not full, meaning that inside FDOS, we have morphisms between von Neumann algebras that are not CPU maps. And inside of FDOS, we also have morphisms between two co-algebras, von Neumann coalgebras, that are not CP-TP maps. So we'd like to restrict the type of morphisms that we're allowed to take to get exactly the quantum-like channels. And the way you would do this in category theory is called double gluing and orthogonality, a la like Hyland and Schock. So the easiest way to restrict what a map can do is to point out what it should preserve. So our new category, which essentially is a category of like quantum coherent spaces, now has objects that instead of like an operator space is an operator space with like a subset of its unit ball that is closed in like an appropriate way for the dual to work nicely. Now morphisms are just morphisms from FDOS that preserves these like kind of distinguished subsets. And since we've used double gluing and orthogonality, we know that our new category is also a model ML in like the right way. And to embed like the Heisenberg category, we can note that a von Neumann algebra and its unit is an object in our new category, and the embedding here is actually fully faithful. So we get between our interpretations of von Neumann algebras inside Q just exactly the quantum channels, exactly the CPU maps. And for the Schrodinger picture or the Schrodinger category, we can note that a phonemical algebra together with its set of like density operators is an object in Q. So this embedding here is also fully faithful, and we get exactly the CPTP maps. It's also worth noting here that both of these embeddings are strict monoidal and preserve finite coproducts or products, depending on like which one you take. So to summarize, we have a model of MAL, which is Q, and then we have two full subcategories, one corresponding to the Heisenberg picture, where the objects are phonemic algebras. We have exactly CPU maps. And now, since these embeddings are monoidal and product preserving, we have exactly that. The two ways of composing phonemic algebras are the two like negative connectives in linear logic. And we have the like opposite thing for the Schrodinger picture. We have phonemic algebras and CPTP maps. And then we have the two positive connectives. Did I want to say anything else? Sorry. No, I think I'm done. Thanks.
Thank you for my thought. Yeah, so you mentioned two relayables, right? But as far as I know, both of them have a star autonomous structure, right? And these are both inspired by, the maps are CPTP or CPMs, right? And you can also make a full subcategory of them and then make about it, then you can get some kind of duality there, right?
Wait, what do you mean?
I mean, it has negations. Sorry. And
what has negations?
So it has a star autonomous structure. So if you take the full subcategory of, for example, like something like first order stuff in it, then you can take the opposite inside that category. You can make another category and take the equivalence of like opposite equivalence, and then you can get something that is dual to CPTP or CPM.
Okay.
Is the point you're making is that these cannot be seen as a CPU in natural way, or is there any problem in?
I'm not sure I understand the question. I'm really sorry.
I'm gonna ask me later. Thank you.
Because I think I would need to like see it like written out.
Nice talk. So I was wondering, so you've got this category, you have this De Morgan duality that's this monoidal equivalence between this category and its dual, and you're able to fully faithfully embed both the category and its dual into this larger category. What does embedding both of these things into this larger category allow you to do? Or like, what's the point of doing that? Does it like illuminate some other properties or something?
What do you mean, like what's the point of like embedding them into a larger category?
Yeah, like what's the point of viewing this like the S and the H as both full subcategories of this larger category?
Is it the fullness that's the issue, or is it like the embedding itself?
Well, I just mean like, why not just view them as sort of like completely separate objects? You have like this category, you have this other category. They have these
because
nice
it's
properties
easier
together.
to work with a bigger category, and also we want like the complete MAL structure, polarized linear logic, without like seen as. If you like just work with polarized linear logic, you need to like go between two categories. Whereas like if you work in MAL, you're working in MAL, and you're working in the same category, I think.
Okay.
Kind of a non-answer, but.
Last question.
So maybe a follow-up question to the previous one. Thanks for the talk. The Heisenberg view is based of stabilized-based algorithms, quantum simulation algorithms, while all the other ones you could say are based on the Schrodinger one. And it's been practically kind of been interesting and difficult to during evaluations, classical simulation, to kind of get to a state where say it would be useful to switch into the other side. possibly because there was no category for data structures to express that. Have you thought about how to basically that could be used to basically for quantum programming, you know, and executing things such you both have the advantages of basically Schroeder style and Heisenberg style representations of operators?
It's interesting, but it's not something that I'm very familiar with.
Okay.
So no, I have not thought about it.
Thank you.
Okay, let's thanks the speaker again.
Hello? Hello? So were they? I think she was trying to turn it up and up and up as I spoke, and then. Got it. Okay, sorry that I didn't notice. So, yes, we would like a language for describing pulse schedules for which formal semantics are possible, so that we can have a verified compiler that outputs them. And here are at least the first steps, we say in this direction. We come up with the name Grampus, a graded modal type theory for pulse schedules. Graded modal is a fancy name for a relatively simple idea. We annotate every variable with a grade or a modality, in this case denoting the moment in time. So negative numbers denote moments in the past, positive numbers denote times in the future. As a simple example to start with, assume we're compiling this quantum circuit on 2 qubits, 1 and 2, and we happen to know with the native gates on this particular quantum chip, Hadamard gate on the qubit 1 takes we know a pulse that implements the Hadamard gate that takes 110 nanoseconds to run, a pulse on the second gate that takes 100 nanoseconds, and the 2 qubit gate takes 500 nanoseconds on both qubits, of course. Then here is a pulse schedule or a program. If you give me a state of qubit 1 that existed 610 nanoseconds in the past, and a state of qubit 2 that existed 600 nanoseconds in the past, then I can give you a state of qubit 1 tensor product qubit 2 that exists now. The types that exist in this language, we have a unit type, we have a label for each qubit in the chip that we are writing pulse schedules for. You can put in tensor products, and we also have a type box DA, which internalizes the grades attached to the variables. So a value of type box DA, if D is positive, represents a value of type A that will exist D nanoseconds in the future. If D is negative, it represents a value of type A that will exist, well, negative D nanoseconds in the past. We can easily produce 2 versions of the language. For those of you, if the colors are visible, then we have the full language, which we call the annotated language, includes these grades for representing the times. And if you put on blue colored glasses, or just take away everything that is colored blue on the screen, we have what we call the plain language, which represents everything with timing information removed, and which is essentially the same as the language of quantum circuits, which is well defined with semantics that are well understood. I will show a very few of the typing rules. So if I know, given inputs gamma, how to produce a value of type A, then if I have inputs gamma D nanoseconds in the future, I know how to produce an input value of type A D nanoseconds in the future. If I know how to produce a value of A D in the future, and from a value of A that exists E in the future, I could produce a B. Well, then if you give me these inputs shifted by E minus D, I could give you a B. We can also apply quantum gates, and you can always just do nothing to a qubit for D nanoseconds. Those are the primitives. The plan for how this all fits together. So we have the annotated language, which has timing information, represents pulse schedules. The plain language, which is essentially quantum circuits. The language before we have any timing information. You can always remove the timing information from a pulse schedule to get a quantum circuit. We know how to interpret a quantum circuit as a unitary in Hilbert spaces. we can compile from the pulse schedule language to the actual inputs that are sent down the input channels to the hardware itself. A hardware model should predict what any given input schedule implements, and so if we have done everything right, then this diagram should commute. The inputs that you get from a pulse schedule should implement the unitary from the associated quantum circuit. This should ideally be a diagram representing 4 homomorphisms between 4 models of our languages. And Lorenzo will explain what we mean by that.
Right. So I intend to start talking about the plain language. Most of what I'm going to say for the plain language will also apply to the...
I think your microphone is off too.
Put it on. Turn it on. Is it on now? Is it working now? Test? Yes. Seems to be working now. Okay. So everything I'm going to say, almost everything I'm going to say about the plain language will also apply to the annotated one. So, as we all know, quantum circuits can be interpreted as unitaries in the category of finite dimensional Hilbert spaces. The key aspect here is that Hilbert spaces form a symmetric monoidal category. The way we interpret types and contexts is relatively straightforward. Unit type is just the complex numbers. A qubit is going to be, well, the two-dimensional complex plane. Tensor product of types is going to be the tensor product of the corresponding Hilbert spaces. And we do essentially the same thing for contexts. For typing judgments, we do roughly what you would expect. I just present the example of what happens for a gate. So, assuming we have derivations for all the terms that we want, you can think of n being either 1 or 2 for 1 and 2 qubit gates. We wanted to present this in a general way. And the way we do it is if context gamma I allows me to deduce ti, then I can just combine them by doing a tensor product and then compose them to, with the unitary that represents the gate. We do essentially the same thing for equality judgments. Of course, the interpretations are going to be built inductively on the, well, typing derivation. An example of the circuit we presented earlier, we interpret first the C naught to the corresponding unitary, and then we interpret the previous stages. We end up with identities, which we can just remove because composing with an identity does nothing. More generally, we can build semantics for the plain language for any symmetric monoidal categories, provided we make some choices. We'd have to decide which objects are going to be assigned to every qubit and which morphisms to assign to every gate. Of course, things have to type check, and then we do essentially the same thing we did for Hilbert spaces. Same example, but now we are using these more abstract symbols. It's essentially the same thing. For what concerns the annotated language, we can roughly do exactly the same thing. The only exception is for gates, because now gates will carry timing annotations. So we have an intended model in mind, which is the one of, well, channels and signals. And the way this works is we construct a category which has objects, sequences of qubits, each one annotated with the time. And then the morphisms are just going to be sequences of electrical signals to be sent to the machines. So for example, here we have a signal that starts 600 nanoseconds in the past and ends now, and another one that starts 610 nanoseconds in the past and ends now. We can generalize this as we did for the plain language. The extra structure we need on our symmetric monoidal category is that of what's called an R module category. So you can think of this as a symmetric monoidal category together with an action of the real numbers under addition. And we want this action to be monoidal so that shifting a tensor product is the same as tensoring the two types shifted separately. Again, the example of the gate rule. It's the same as what we did before, but now we have to shift everything by d, where d is, of course, the time it takes to perform the gate we are talking about. Everything goes through inductively in exactly the same way, and things work out for equality judgments as well. It turns out that we can prove quite a few interesting and expected properties. We can prove soundness and completeness. We can construct models from the syntax of each of those languages. And from this, I'm pretty sure we can also deduce normalization, even though we don't list it here. If the hardware model is correct in the appropriate sense, then the diagram that we showed earlier just commutes. So, in conclusion, we defined languages that can describe pulse schedules and can also describe scheduling strategies. So that, for example, deciding to schedule something as soon as possible or as late as possible or some mixed choice are going to be different, at least syntactically different. We are working on building a verified quantum compiler, which is on the URL shown here. The next step that we want to think about is how to add measurement for this. Because once we can add measurement, we will most likely be able to have full classical control, almost out of the box. This whole talk has been inspired by it's based on a preprint that we have on the archive. That's the link. Credit to how we found the name, we used acronymify online. So if it sounded weird, that's the reason. And yeah, that's it.
Thank you. Questions?
Thanks. Thank you for your talk. That's really cool. So one thing that I noticed from the types is that it seems to be assuming that you can always do nothing to a qubit. You can extend it into the future. Have you had thoughts about how to capture the idea that doing nothing to a qubit is, can affect the semantics, cause decoherence and things like that?
That's the problem, of course. It could just be the qubit alone, then this would not be a difficult problem. The different schedule strategies would all do exactly the same thing.
But that's the reason why we have this delay operation here. This is not the identity, not at least by definition. When we erase, it becomes the identity unless we extend the unannotated language with fake gates which represent those delays. And that also just works because we didn't make any assumptions on the gates. So we can have an infinite family of delays for each qubit, if that makes sense.
So delay is some morphism from the qubit now to the qubit d in the future, not necessarily the identity.
So does the soundness property that you described in terms of this commutativity, that doesn't account for those delays though, right? Because in the erased program, it's just doing nothing.
Oh, I see. Yes, this is on the ideal quantum computer.
Yeah.
Yes, in this
Yeah.
model, yeah.
Yeah.
That's what we're talking about. Yes, if you include noise in your hardware model, then you're talking about how closely it approximates the target unitary instead.
Thank you very much.
I think we have time for one more quick question.
Hi, thanks for the talk. I found it really understandable. You had so I think on the last slide you said that the graded modal language is can't. Yeah, you said it describes pulse schedules. I was wondering how tight this correspondence is. So from every term of your language, you can get a pulse schedule. Is every correct pulse schedule, does it have a definition in your language, and is it one-to-one? And yeah, does that make sense?
Every pulse schedule can be represented in the language, straightforwardly. It is not, well, it's one, it should be one.
Well, every consider that you can build by the signals that you know represent a given gate. And every one of those corresponds to a program language. The ones that are built in a different way.
Sure.
Is it one-to-one up to definitional equality? Not necessarily. No, that doesn't follow just from completeness. I think it should be, assuming that there are no equations between native gates. Like if by coincidence the native gate correct sort of outlines the same as some of the native gates. Good question. I think it should be, yes.
Thank you.
We haven't tried to prove it. All right, thank you very much.
A unified assertion-based framework for classical quantum program verification. All right, take it away.
I'm Inter from Micron Institute, and this is actually a proposal for my new idea of how to implement a tool for classical quantum program verification, and it would be easier to follow. So background, we have quantum algorithm, and we encode it into programs, and then it is compiled into circuits, and circuits are mapped to device and executed. So when we talk about verification, we talk about the second part here, because after this part, all the procedures are automated, and the encoding part and the proof for algorithm can be error-prone. So here, the verification is actually symbolic, and our goal, when I consider this work, is to push the frontier of symbolic verification on real-world examples. Actually, this starts from story about a failure. This year, we also had a submission for POPL. It was about classical quantum, relational Hall logic, a very complicated concept. And I was in charge of the implementation part with almost the same goal as above, to actually build a tool that can implement, that can encode real-world cases. And the tool was in trouble with many reasons. One reason is the logic is complete, but the rules are too abstract and they don't provide constructive transformation. They cannot be implemented. Another reason is the tool cannot be used intuitively. The predict language we are using is really hard to encode and hard to parse. And also the way we implemented it. So we choose to do it in OCaml, thinking it would provide us more control over the tool, which, however, turned out to be technical debt. So in the end, I'm not sure how reliable the tool is. And we had to hack the tool to encode specific particular examples. So the tool was doomed, I thought, and then the result turned out as expected. But sometimes failure teaches more than success. And all the reasons, after I have been thinking about it, it can be concluded as one. So research papers ask for novelty, but building a good tool asks for something different. So what do we really want if we consider from the user's perspective, from the tool? I think we need a general, elegant design and intuitive, cognitive, aligned, usable tool implementation. That's the goal. It's not about something novel. But to achieve this, we need to make multiple design choices correctly. So there are several challenges. One challenge is the classical quantum methodology. What is it about? We want to introduce classical variables into quantum programs because many algorithms involve classical variable and their computation. And also, if you know that some variable are classical, you can represent and reason about them efficiently. But the problem is, how do you represent the classical quantum program state? So the method we have been using is directly taken from this paper, the first paper on the topic. It uses mappings as states. What does it mean? So here is a simple demonstration. You have two sets of variables. One set, for example, x here is classical, and the other set, for example, q here, it is quantum, and they're separated. And for example, here q is in superposition. After measurement, you get this state. So here, actually, the classical state and quantum state are correlated. And mapping means we use the mappings from classical program states to the quantum program states to represent the classical quantum program state. So this is the idea. It works. It works in theory. But if we implement it in implementation, there are some problems. Like, what is the context? What is the syntax for the mapping? And also, the extra wrapping of mapping will make the reasoning very complicated. Also, if you use mapping for states, then when we talk about logic, when we talk about predicates, you also have to use mappings. And this is where the nightmare happens. So you really can't encode the intuitive idea, the description of states into that kind of predicates. So after some thinking, I think the problem can be solved by subtyping a different perspective to view this problem. One principle: all variables are fundamentally quantum, even if you consider classical variables, and they can be identified by types. So what do I mean by classical? Here, some setting for the program language, but essentially, when you have a register which consists of a set of variables, and the state satisfies the property that after measurement on this register, the quantum state stays the same. Then we can say that the register is classical. So here actually, classicality becomes a property to be satisfied. It is not something that is separated from quantum. So that's the idea. And by identifying these special registers, we can make use of the classicality and simplify the reasoning about the classical part as well. Yes, the classical part can be identified by context and typing. The context should be, of course, declared when you define the program. And another important theoretical result as a conclusion is that this method is isomorphic to the mapping method, meaning that this way of representation and symbolic reasoning has arguably the same complexity. And this is about states. And if we move on to consider predicates, things are more chaotic. So there are different ways to describe the property of quantum states. One way is use subspaces, and we decide whether one quantum state satisfies the subspace or not. This is called the qualitative way, and the other way is the quantitative way, where we use observables and we talk about the expectation of quantum states on the observables. But they all have their drawbacks. For example, the subspace way cannot describe properties, and the observable way, the quantitative way, cannot express logic connectives. So, okay. So in short, if we start from our intuition, we want to write something like this. So we have classical part and quantum part. We can combine the predicate on this. And this we can design a language for this. This is similar to Boolean algebra. But the difference is that we have a special terminal term here represents the subspace, actually the one-dimensional subspace. And the semantics is also different. They are not interpreted into Boolean algebra or Boolean lattice. They are interpreted into subspaces. So we are still using the subspace style predicate. And they are described by also modular lattice. So here is the trick. Also modular lattice is a generalization of Boolean lattice, and the only difference is that they do not obey distributivity. So subtype comes again. Boolean lattice is a subtype of also modular lattice. And about decidability, also modular lattice it's a still open problem about it, and we want to use existing tools like SMT solver to solve the classical part because they will be blended together. And in short, this can be decided by typing. So you can identify which part recovers the property of Boolean lattice, and you can utilize this fact to do proof nicely. And here is an example from our real work. So x and y are classical variables, and here R is a quantum register. These two predicates are identical. They are reasonable, but how to prove it? The trick is that we can identify the parts x equal to y as commuting to the two subterms of disjunction. And this means the distributivity recovers, which is not always the case for osmomodular lattice. And then we can put the x equal to y into the two subterms. And then the classical reasoning will tell you that you can replace one with the other. So this is an example of how subtyping can help you build a predicate language that fits your intuition and can be proved easily. So this is about predicates. And the next part is assertion, language, or logic, implementation, and automation. So they are really like a problem that involve these entangled parts. What is the best environment to do program verification? I would say for quantum it is definitely interactive stream prover. The reason is that for classical program verification we have the SMD solver. So it can prove the relation between predicates automatically. But for quantum, the proof involve a lot of mathematical parts. But the problem, or the opinion I have is in interactive stream prover or logic, actually it should be considered as a proof technique instead of something that you must rely on. So different from like implementing a program verifier in C++ or OCaml, where you must rely on Hall logic. Otherwise, if you cannot encode your property in the logic, then you cannot deal with it, you cannot prove it. It's not the case for interactive stream prover because the logic foundation has changed from Hall logic to the type theory. And actually you have Hall logic and the semantics of the language formalized in interactive stream prover. So think about it in this way. Even if you have a very complicated, very special property of correctness that cannot be encoded using Hall logic, you can still encode it using semantics and try to prove it. Although the proof would be tedious, obviously, but automation will counter this problem. And we all know that artificial intelligence has been proved to be really good at it. So the thing I want to say is that when we do it in interactive stream provers, the first priority is not to build a complete Hall logic. The first priority is to design a general language that can express your correctness property nicely. And what do I mean by generally and nicely? Here, this is my idea, and actually it follows the research result from GeoBot and Robert Rand for publicity programs. So basically, we have multi-level assertions. Here, P here is the subspace predicate we have been talking about, and E is the value expressions, meaning that intuitively, when we express the property, we talk about expectations and arithmetic operations on these expectations. And the real predicate, the real assertion we talk about is we compare the expectations in different ways and compose the comparisons. So also this is general because it allows you to talk more. It allows you to describe your intention better, and also it aligns with intuition. So then with this kind of assertion, we can like compare different ways to design the Hall logic. This is the classical one. Notice that here the implication is a classical one. And for the Hall logic, the quantum Hall logic we have been using, it is actually not implication, it is the comparison between the expectations. So here, I want to make a point that in this quantum Hall logic, we are actually hard-coding the special kind of correctness property we want to prove, that is comparing the expectations. We hard-code it into this kind of quantum Hall logic. And if it does not follow this pattern, then we cannot prove it. For example, when you want to consider concurrent programs, or when you want to prove by separation logic, you want to have like the conjunction, disjunction between the predicates. It's not possible here. But with the multi-level assertion-based horologic, we can do it. And actually, in form, it recovers the simplicity of classical deterministic horologic. And one fact is, actually 2 can be embedded in 3. So, to conclude, you may ask, what does the final product look like? I imagine it should be a lean project, formalizing the language with assertion language, semantics defined, and horologic is a proof technique. And also automation, I haven't mentioned it, but it's really important to make a usable tool. We should have automation, and it should demonstrate through real-world examples. For example, take show algorithm and encode it using the programming language and prove the correctness. And also a natural, like future work, a work in the future is we can consider compiling the programming language into target circuits. So key takeaways: use subtyping for classicality, and we should unify class quantum predicate by osmodularities. And for assertion language, use subtypes with multi-level assertions. And for verification in interaction provers, so the first priority is a general and expressive language. So that's my opinion and the blueprint for the implementation in my mind. And I'm happy to hear your suggestions and comments. Thank you.
All right, thank you. Questions? Okay, I'll start off. So your recommendation there seems pretty similar to COQ, I think, because COQ is, it's a verification framework in the ROC Proof Assistant, but I believe that most of the actual proofs they went through a horse-style logic. So can you talk a little bit about the similarities and differences there?
Thank you for the talk. I was just wondering about the classical world clashing with the quantum world. At the bottom of it, sometimes it seems that it's like the disjunction as an idempotent operator clashing with the world of linear algebra, where you have plus, which is non-idempotent, but you can. So in other words, Boolean rings versus Boolean algebras, or saying instead of having disjunction, but having XOR as a primitive, because then you could say like, oh, what's a predicate? I was just thinking, what's a predicate that's not 0, 1, maybe just mapping into a base field, K. It's like, and then it's an element of the dual vector space. So a predicate would be in this fashion embedded into the spaces of quantum-like computing. Do you see these things in practice popping up? Is like having disjunction being a nasty thing to deal with as a primitive?
You're asking whether we really need this disjunction.
Well, you can code it, right? But you know, having as a primitive XOR basically, and then just saying, oh, this junction is very complicated. You know, you have to just code it in terms of XOR and one minus and so on.
So
right?
you mean that in classical logic there is a famous result that you can use XOR to encode everything? Maybe
yeah, it's more like the difference between Boolean rings and Boolean algebras, because the Boolean rings you have an additive inverse, right?
Well, okay, that holds for logic, but I think we can like consider the problem in different perspectives. So as Leo, the developer for Link said, you have to work on the correct level of abstraction. So here I'm talking from the lattice level, because in the lattice you have the joint, the joint meet, and they are defined by the conjunction and disjunction. So there is a very close connection between lattice, the algebra representation, and the logic part. So that's why we don't consider it all here. So it's natural to use this in algebra. That's why. Yes.
Lattice algebra, right?
Yes.
Yeah.
Yes.
Okay. Thank our speaker again. So now we're going to go to our first remote talk of the day, which is always an exciting technical challenge for our video staff.
Can you hear us? Can you hear us? I think you are muted now.
Yeah, hello. Can you hear me?
Try to speak again.
Hello, hello.
Okay, are you getting it? Okay, you can start.
Okay, our talk is a pulse level DSL for real-time
so
quantum control. Go ahead.
I can hear you right now, so. Oh.
Go ahead.
Can you, no, with this. You should hear us, and we are hearing you, so if it's okay, you can start.
Well,
You
I
sure
cannot
that it
hear
is
anything
now?
on my side. Okay.
Okay, I think you
Okay,
can
great.
start.
Yeah. Thank you. So, yeah, hello everyone. I'm Yushen Wu, and I'm glad to be here to present our ongoing work, a post-level DSL for real-time quantum control with hardware compilation and emulation. In collaboration with Yue Shi, Jing Liu, and Yu Xiangpeng. I was affiliated with Academia Sinica at the time of submission, and I'm now a PhD student at Purdue University. Before I start the presentation, I would also like to thank PC Chair and the AV team for supporting us with the remote presentation. To start, let me try to persuade you why real-time quantum control is important. To understand this, it helps to look at what actually happens during a quantum computation. The first example is repeat until success, or RUS. In this circuit, we apply an operation, measure an oscillar qubit, and based on the outcome, either accept the result or repeat the procedure. This means the computation inherently involves a loop. Measure, decide, and immediately act. Without real-time control, the system cannot conditionally branch or repeat operations fast enough, and the assembly cannot be executed as intended on real hardware. The second example is quantum error correction. Here, synchrone qubits are measured repeatedly to detect errors, and the results are used to infer corrections or update the polyframe in real time. These feedback loops must run continuously and with very low latency. Otherwise, errors accumulate faster than they can be corrected, undermining fault tolerance. Together, these examples show that quantum computers are not just executing static circuits. They rely on real-time, feedback-driven control to tightly couple measurement, classical decision-making, and physical quantum operations into a coherent system. Next, I want to show you why real-time quantum control is a programming language problem. At its core, quantum control is not just about controlling hardware. It's about expressing real-time feedback and branching, where measurement results immediately influence future actions. This already goes beyond static circuits and looks much more like a reactive program. At the same time, quantum operations must obey deterministic timing and concurrency. Operations run in parallel, start at precise times, and must remain synchronized down to the hardware clock. This is a scheduling problem, not just a physics one. Finally, semantics matter because quantum physics is continuous. Small timing differences or ambiguous interpretations of a program can lead to physically different outcomes. If the language semantics are unclear, the experiment itself becomes ill-defined. For these reasons, real-time quantum control is best understood as a real-time, concurrent programming language with hard timing constraints, rather than as a static circuit description. So why do we focus on post-level control rather than gate-level abstractions? The core reason is that gate-level models do not natively capture precise timing. In real quantum hardware, the system is always evolving under a continuous Hamiltonian, even when we are not actively applying gates. Any delay, jitter, or ambiguity in timing can physically change the outcome of the experiment. It's especially critical for microsecond scale or even nanosecond scale feedback loops. Recalling the previous two examples, RUS circuit and quantum error correction. Here, measurement, classical computation, and control pulses must be tightly synchronized with deterministic latency. Gate-level descriptions hide these timing guarantees, making it impossible to reason about correctness. At the post level, we can explicitly specify waveforms, giving programs unambiguous real-time semantics that match the underlying physics. And this is why we need post-level tools for real-time quantum control system. Given the motivation, the next question is, what is missing in today's post-level tools? The first issue is opaque control hardware. Many existing systems hide critical details behind fixed APIs or firmware layers. As a result, programmers cannot reason about latency, scheduling, or how control decisions are actually executed on hardware. Second, most post-level tools are vendor-specific. They are tightly coupled to particular hardware platforms and evolve according to product needs, not long-term language design. This fragments the ecosystem and limits portability, reproducibility, and cross-platform experimentation. Finally, we see ambiguous language constructs. Current POS interfaces often lack clear semantics for timing, concurrency, and real-time feedback. It's difficult to tell when POSes truly start, how parallel operations interact, or how long classical computation is allowed to take. From a programming language perspective, this makes programs hard to reason about and even harder to verify. Taken together, existing tools provide low-level access, but not a principled programming model. What's missing is a post-level language with clear semantics designed explicitly for real-time quantum control on open hardware. Before moving to the framework, I want to briefly highlight the programming language principles that guide our design. First, we aim for precise semantics for timing and concurrency. Time is an explicit semantic dimension in our model, giving deterministic meaning to parallel POS execution and to the interaction between control computation and POS scheduling. Second, we support first-class real-time control. Measurement, branching, and feedback are treated as core language constructs with well-defined operational semantics rather than external mechanisms. Finally, we focus on portability across heterogeneous hardware by separating program meaning from execution. The same program denotes the same behavior, while compilation handles hardware-specific realization. Together, these principles enable clear reasoning, portability, and reliable real-time execution for quantum control programs. To address those challenges, our work proposes a complete end-to-end stack for real-time quantum control. The key idea is that no single layer, language, compiler, or hardware can solve this problem in isolation. We need a system where all layers are designed together. At the top of the stack, we introduce a post-level domain-specific language. This language is designed around the realities of quantum control: real-time feedback, conditional branching, deterministic timing, and explicit concurrency. The second layer is a compiler that translates these high-level control programs into low-level binaries executable on control hardware. Finally, we have the quantum control hardware and the quantum device. The quantum control hardware prototype we use is radio frequency system-on-chip. As you can see, there is a CPU, the signal generator, and decoder, and it connects to the quantum device with DACs and ADCs. In this framework, we provide an emulator that co-simulates both the control hardware and the quantum device. This is crucial because real-time bugs are often about timing, latency, and race conditions, issues that are extremely difficult to diagnose directly on lab hardware, not to mention the considerable expenses. With the emulator, developers can test, debug, and validate control programs before deployment. Together, this stack turns real-time quantum control from a collection of hardware-specific scripts into a programmable, analyzable, and portable system, grounded in clear semantics and practical execution. We believe that this structure will serve as a guiding framework for the next 5 to 10 years. Let's take a look at the top layer, a post-level domain-specific language. To understand our DSL design, let me first explain what is required for post-level programming. At this level, we are no longer describing abstract gates, but directly controlling physical signals. A program must specify waveforms, including their amplitude, phase, frequency, and duration. It must also express when pulses occur, which channels they run on, and how multiple pulses execute concurrently without conflict. In addition, post-level programs must integrate real-time control. This includes performing measurements, using the results in classical computation, and making control flow decisions that immediately affect subsequent pulse execution, all under strict timing constraints. With these requirements in mind, our DSL combines classical control constructs with pulse-level operations. As you can see, the syntax reflects this structure. We provide familiar constructs such as sequencing, conditionals, and loops, alongside primitives for defining pulses, playing link on channels, running operations in parallel, and performing measurements with feedback. For semantics, I want to mention some of the key ideas. First, we decouple CPU time and scheduler time. Classical control execution advances CPU time, while physical evolution is governed by the pulse scheduler. These two notions of time are independent but coordinated. Classical computation does not directly advance physical time, while pulse execution can constrain and synchronize control flow. Second, pulse execution follows an as soon as possible scheduling paradigm. As the program runs, pulses are dynamically scheduled at the earliest valid time based on the current scheduler state, and the schedule is incrementally constructed during execution. Third, we support explicit parallelism. Pulses issued on different channels can execute concurrently, while pulses on the same channel are automatically serialized. Parallel pulse blocks synchronize by waiting until all involved channels complete before continuing, giving deterministic and well-defined concurrency. Finally, while the semantics are hardware independent, execution depends on hardware specifications such as available channels, timing resolution, and latency. Together, these principles allow us to reason precisely about timing, concurrency, and real-time feedback in pulse-level quantum control. Next, I want to talk about how we connect the DSL to real hardware. The compiler translates high-level pulse-level programs into low-level RISC-Q binaries that can execute directly on control hardware. Classical control logic, pulse definitions, scheduling decisions, and real-time feedback constructs are lowered into instructions that run on an on-chip RISC-V-based controller. Rather than building a compiler from scratch, we build on an existing plain toolchain and extended with support for explicit memory manipulation required by quantum control. These extensions allow the generated code to interact directly with memory-mapped control components, such as pulse generators, DACs, ADCs, and scheduling buffers, in a precise and predictable way. The resulting executables are designed for low-latency execution and can run directly on RF-SOC-based controller. In this way, the compiler serves as a concrete bridge from high-level pulse-level programs to deterministic real-time hardware execution. The last component of our system is the emulator, which is essential for validating real-time quantum control behavior. A key property of our design is that the same compiled RISC-Q binaries run both on real RF-SOC hardware and inside the emulator. This means the emulator executes the exact low-level control logic produced by the compiler, rather than a rewritten or abstracted model. On the control side, we use validator to simulate an RF-SOC architecture, including a RISC-V CPU, DACs, and ADCs, all operating with realistic clock rates. Pulse generation, measurement, and scheduling are executed with the same timing behavior as on hardware. In fact, you can think of this part as a control board. For example, we're currently working out including AWGs. On the control side, we integrate a quantum device simulator that evolves under a continuous Hamiltonian, driven directly by the pulses emitted from the control simulation. The two sides communicate through real-time FIFO-style interfaces, closely mirroring how control electronics interact with physical devices. This co-simulation allows us to study end-to-end behavior, such as feedback, latency, synchronization, and race conditions, before deploying to lab hardware. As a result, the emulator provides a practical bridge between language-level design and real-world quantum control execution. To demonstrate the practicality of our language and tool chain, let me show you an example, Rabi oscillation. We use our DSL to generate resonant drive pulses that induce coherent oscillations between the qubit's energy levels. The pulse parameters, such as amplitude, phase, frequency, and duration, are explicitly specified in a program, and the duration is varied across iterations. The compiled binary runs inside the emulator, where DAC-generated pulse drive the quantum simulator through a continuous Hamiltonian evolution. The measured population exhibits the expected oscillatory behavior, matching theoretical predictions, which confirms that our scheduling, timing semantics, and pulse executions behave correctly. With this case study, we can show that our framework can faithfully express and execute realistic pulse-level quantum control programs while preserving precise timing, concurrency, and real-time feedback across the entire stack. In conclusion, we present an end-to-end framework for pulse-level real-time quantum control. Our system provides a principled programming model, compiles high-level control logic into low-latency hardware binaries, and supports co-simulation through an emulator that executes the same code as real hardware. Together, this work establishes a foundation for precise, predictable, and portable real-time quantum control grounded directly in physical execution. And that's all for today. Thank you.
Hi, thanks for the talk. So you talk about this being portable, but pulses and durations are highly hardware dependent, right? So what does that really mean?
Yeah, so let me, yeah, okay. So our idea is that because this language is designed with a, okay, so you mentioned the portable one, right? So you can think that the current control hardware is like, you know, there's many different kind of quantum control hardware, but our language design is basically we want to make it portable that across the heterogeneous control hardware. So here you can see that we basically frame what a pulse level programming should look like in our syntax and semantics, which base our you know leads to our language design.
Okay, let's thank our speaker again. And I think we're going to go to our next remote talk.
Hi, can you hear me? Okay, can you see the slide now?
Yes, we are seeing the slide.
Okay, then I'm going to start. Okay, hi everyone, I'm Shen Yang. Today I'm gonna share our work, quantum assertion testing without mid-circuit measurement, strategies and law bounds. It's a work done by me and Charles Xuan, and we are from University of Wisconsin-Madison. So our topic here is quantum assertion testing. But first of all, why do we even want to test quantum programs? Well, it is because quantum programs are really hard to reason about. Here's an example on the Grover's paper. On the left, you can see the algorithm as it was described in the original Grover's paper. And on the right, there's a version written in one of today's most high-level quantum programming languages. Well, this is a little bit complicated. The fact is, in this algorithm, we see things like loops, function calls, and array accesses, and those are exactly the kind of places where bugs can show up when people try to code them. So I'd argue that it would be really useful if we could test these programs by inserting runtime assertions to check the program state, just like what we do when debug classical programs. As we know, in quantum computation, we are manipulating qubits, which is usually in a superposition of kit 0 and kit 1. It only collapses to a classical 0 or 1 when we perform a measurement on it. So this means we can't really learn anything about a quantum state unless we actually perform a measurement. Now, if we think of executing a quantum program as applying a sequence of quantum gates on qubits, and imagine we've inserted some assertion circuits, these little black boxes, into the circuit. Then to check whether the program state satisfies some certain predicate during runtime execution, the most straightforward idea is to just measure those qubits. But we generally don't want to do that, because measuring the program qubits would collapse their states, which usually disturb the rest of the computation, and that's a problem if we want the program to keep running correctly. So to actually learn from assertions in a quantum program, prior works have proposed to use ancilla qubits to get toggled when an assertion fails. Then, instead of measuring the program qubits directly, we just measure those ancilla qubits. For example, here we have two ancilla qubits, each get toggled by the outcome of one assertion at runtime. Then we can defer the measurement of these two ancillas till the end of the program. Another thing we might want to do is to reuse the same ancilla for multiple assertions. The idea is you measure the ancilla in the middle of the circuit to check one assertion, then reset it to cat 0 and reuse it for the next one. That sounds nice. It saves ancilla qubits by recycling the same one each time. But here's a catch. This approach relies on mid-circuit measurement, which means performing a measurement in the middle of the quantum circuit. And such physical operation is inefficient and can be hard to support in current quantum hardware, so we might want to avoid that if possible. And this brings us to the core question of our research. For a quantum program with n assertions, we want to understand, without the use of mid-circuit measurement, how many times we need to run the program and how many ancilla qubits we need in order to detect whether any assertion fails, and also to identify the first failing assertion. We call these two problems the exist fail problem and the first fail problem. In classical computing, it is trivial. No matter how many assertions in a program, a single run with one bit of outcome is enough. While in quantum setting, things are much less obvious. One of our key results is that if we consider a single run setting, then for both these tasks, first fail and exist fail, the required space overhead has a tight seed-login bound. Now, to better illustrate our motivation, let's look at a few very simple quantum program snippets to get a feeling of what kind of assertions we might want to test during runtime. For the first example here, x is an arbitrary qubit, and we initialize y to kit 0. We apply a CNOT gate controlled by x and targeting y. After this operation, the result is alpha kit 00 plus beta 11, and this is a typical entangled state. So at the end of this code snippet, we might want to check whether in each branch x equals y at runtime. And if we had a way to perform assertion checking like this, say assert x equals y, then it should give us a pass if the code does not contain any bug. In the second example, we start by preparing z in the cat 0 state, and then we apply two consecutive hard gate on it. And the final state will still be in cat 0, so we might want to write an assertion like assert z equals 0 to debug the code. For the third example, the only difference from the previous one is that we add a phase flip, a z gate, right in the middle of the two hard gate, and it's controlled by a classical input bit. With that, the final state of the qubit y ends up matching the classical input bit. So if we assert y equals 1 here, then it will pass if the classical bit is 1 and the program is correct. Now what we really care about is that if we combine those three code snippets together into a single program and put the three assertions we want to check exactly where we want to check them at runtime, now we have three runtime assertions in a single quantum program. As we mentioned earlier, in such situation, we don't want to directly measure the program qubits x, y, or z at those assertion points, because that would collapse the state and disturb the rest of the computation. So how do we actually check these assertions? Well, the trick is to route each assertion's runtime outcome into an ancilla qubit, so that we don't have to measure the program qubits directly. Instead, we can just measure the ancilla qubits to learn the outcomes. Here, for each of the 3 assertions, we use an oracle unitary to write the assertion's runtime outcome into an ancilla qubit. The exact design of these oracle operations, these O1, O2, and O3 shown on the slides here, depends on the type of those assertions we want to check. For example, the oracle for the first assertion A1 consists of performing 2 CNOT gate targeting an ancilla A, and the oracle for assertion A2 and A3 can be instantiated by a single CNOT gate targeting their corresponding ancilla qubits B and C respectively. Well, existing literatures on quantum assertion have studied this in detail. They have studied the expressiveness of assertions and how to realize the checking for them at runtime, which gives what these oracle unitaries actually look like. But in this work, we just treat them as oracles, and we don't care about their exact circuit structure, and simply assume such oracles exist and can be invoked. Then we can simply defer all measurements of these ancillas to the very end and learn all 3 assertion outcomes within one run. If we generalize this approach to a quantum program with n assertions, we will use n ancilla qubits, each get toggled by one assertion outcome. This is what we call the single-run n ancilla strategy. In this strategy, we only run the program once, but with n ancillas. Do we have other options? Well, instead of running the program once with n ancillas, we can run it multiple times, each time enabling only one assertion, and just use one ancilla to store that outcome. So in the first run, we enable only A1 using a single ancilla to capture its outcome, and then measuring it at the end of this run. And in the second run, we enable A2, reuse the same ancilla A, and measure it again at the end to learn the result. And in the third run, we do the same thing for A3. So overall, we reuse one ancilla across multiple runs and learn one assertion outcome per execution. And this is what we call single ancilla n-run strategy for a program with n assertions. And now let's take a close look at these 2 baseline strategies we described and consider the resource used. Both strategies satisfy the trade-off of form t times s equals On, where t is the number of executions, and s is the number of ancilla qubits used per execution. And the natural question to ask is, can we have a strategy that achieves a better of all trade-off? Well, one thing we may want to do is that if we allow mid-circuit measurement, and we can reset measured qubits for later use, in that case, we can reuse the same ancilla for every assertion within a single run. This idea is, after each oracle invocation, we just measure that ancilla immediately to learn the assertion outcome, and then reset it back to fresh, so it's ready for the next one. For example, here we only use the same ancilla A 3 times, and measure it 3 times during a single run. And this approach uses only one ancilla and performs just one run for all n assertions. This seems to be a better solution. However, such strategy relies on mid-circuit measurement, and a previous study have shown that this physical process, measuring qubits at the middle of the circuit, is kind of slow and relatively hard to support in current quantum hardware due to latency and noise sensitivity. And that is why we may want to avoid doing that if possible. And our work is to discuss if we could design a better strategy to learn from runtime assertions without the use of mid-circuit measurement. In our problem setting, we consider a program with n-indexed assertions, A1 through AN, each inserted at a different point of the program. In terms of the semantics of each assertion, we abstract them as assertion checking oracles. The definition of this oracle is shown on the slide. It applies on the program state psi and an ancilla qubit AI. The oracle keeps the ancilia unchanged for the assertion passing branch, but toggles the ancilia failing branch by XOR the value of the ancilia by 1. From this definition, we can see that, depending on the bucket program and the assertion, the outcome of the runtime assertion may not be a deterministic 0 or 1, it may instead be in a superposition of pass and fail. While in this talk, for ease of presentation, we restrict attention to the case where the assertion outcome is deterministic. For the more general case, where the outcome can be in a superposition of pass and fail, we can declare an assertion to fail when the state has some failing amplitude, then detect via efficient sampling. We will include the detail of such kind of discussion in the next version of our paper. We then define our single run and multi-run strategy. A single run strategy is basically an instrumented execution of the program. This instrumentation has to specify two things. First, which assertions are enabled in this run, and how the assertion checking is carried out. More concretely, it includes how we initialize the ancilia pool, and then for each enabled assertion AI, we invoke the oracle unitary OI to write the assertion outcome into some chosen ancilia qubit. And after that oracle call, the instrumentation can also apply an arbitrary unitary UI on the ancilias to do whatever additional computation it wants. At the end of this run, we measure the ancilias used in this execution and obtain some classical bits. For a multi-run strategy, we simply allow multiple such instrumented executions, and we further classify multi-run strategies along 2 dimensions: whether the enabled assertion sets are disjoint across runs, and whether adaptivity is allowed. Now let's talk about some of our results. First, consider the exist problem in the single run setting. In one execution, we want to detect whether any of the n assertion fails. For this problem, the space law bound we established says that we need at least omega log n ancilia qubits. Well, this is a little bit surprising because information theoretically, the answer is only 1 bit, failing exist or not. The reason we still need log n space here is that the computation on the ancilias has to stay reversible. For the proof of this law bound, we look at a canonical program where the program qubits holds a length n 0-1 bit string w, and the program itself applies just identity throughout the execution. For the n assertions, we define that the ith assertion to simply check whether the ith bit of w is 0. And the overall effect of assertion checking gadget OI plus UI on the ancilla register for this program can be seen as performing one of the 2 permutations, PI0 or PI1, on the ancilla spaces state, depending on the ith program bit being 0 or 1. At this point, the exist fail problem reduces to a problem on a finite state permutation automata. The number of automata state is the number of ancilla basis state. The automata reads an input bit string w of length n, which just corresponds to the bit string stored in the quantum program. And when the automata reads the ith bit, it updates its state by applying either PI0 or PI1. So the question, how many ancilla qubits do we need for exist fail, now becomes how many state do we need for this permutation automata to compute the ON problem. For this problem, we prove it needs at least n plus 1 state. The proof has 2 steps. We first prove a pumping style lemma, then we use a counting argument which considers inputs with different O0 prefix. We show that the automata must end in pairwise different state after reading such kind of inputs. Putting this together, we get that the automata needs at least n plus 1 distinct state. This means we need at least omega log n ancilla qubits. For the upper bound of the exist fail problem, we gave a strategy that uses a mod n plus 1 counter with all log n ancillas. So this log n space bound is tight. Next, still in the single run setting, we look at the first fail problem. In one execution, we want to identify the position of the first assertion that fails. We show the ancilla law bound is also omega log n. This can be proved by either reducing from the exist fail law bound or more directly from an information theoretic counting argument. And as I'll mention on the next slide, for first fail, we can also construct a strategy that matches this log-on bound. So unlike exist fail, here requiring the computation on the NCLS to stay reversible does not impose extra restriction for this problem. Here we provide one possible construction with all log-on space for the first fail problem. In a single run, we use two pieces of NCLS, a 1-bit flag qubit F and the index register whose size is log-n plus 1 qubit. Then for each assertion we encounter, we do 3 steps. First, we call the assertion checking oracle to write the assertion outcome into the flag F. And next, we do a controlled update on the index register, controlled on F. If F equals 1, we swap the all 0 basis state with a basis state that encodes the current index I. Notice that such kind of operation is reversible. And finally, we uncompute F back to 0, so we can reuse the same flag qubit for the next assertion. In the end, the index register contains exactly the binary encoding of the first failing assertion, I star. Finally, I want to give a brief summary on our results for multi-run settings. If we consider disjoint assertion sets and allow adaptivity across runs, then we show a lower bound for both problems of the form 2 to the s times 2t equals omega n, and we further show this lower bound is tied for both problems. And if we consider general assertion sets but no adaptivity across runs, then we establish a lower bound of a different form, which is s times 2t equals omega log n for both, and we further show for exist fail problem this is tight. For the details of the multi-run setting, please refer to the next version of our paper. So to sum up, we initiated the study of time-space trade-offs for checking multiple assertions in quantum programs without mid-circuit measurements. And we established non-trivial lower bounds and strategies for the exist fail and first fail problem under different settings. In the near term, it would improve our ability to test quantum programs on hardware platforms where mid-circuit measurement is costly or unsupported. And in the long run, the strategies we propose also require fewer measurements compared to mid-circuit measurement strategies. And that's it, end of my talk, and I can take questions.
Questions?
Thank you for your talk. It was so interesting. But I might say something like very stupid. But does it make sense to assume, for example, like at most one failure can might have occurred, can occur, and like improve the strategy or something like that?
So we don't need to assume that at least one failure occurs, because you see we have the problem of deciding if there has any existing failure.
Yeah.
So if there is no existing failure, then the existing fail problem should give us the result that there is no failure.
Okay, thank you.
All right, let's thank our speaker again.
Thanks for the nice talk. What could you say about extending this to non-linear lambda calculus? To non-linear lambda calculus or to recursion?
But, okay, you hear me? Yes. Okay, so hello everyone, my name is Will Schober. I'm a PhD student at the Università della Svizzera Italiana in Lugano in Switzerland. And this is a joint work with Scott Wesley from Dalhousie University in Halifax, Canada. So I'm going to be telling you about this thing that we call a hierarchical circuit language, which is really just a kind of slight extension of quantum circuits that capture a couple interesting things, in particular control, or describing controlled operations as a composition. Okay, so for a bit of motivation, okay, there's several motivations here, but maybe one of them is for control flow. So on the left, I've got the same diagram that we saw in the keynote speech. This is the coprocessor model, where the idea is that you have a CPU that is sending instructions to a QPU, and so inside that CPU would be a programming language. It has classical control flow, it has a compiler, and so on, and it's just sending unitary instructions to be carried out on a quantum processor. So like on the right side here, I've got some examples of things you can do, or rather 3 examples of things you can do and 1 example of a thing that you can't really do. So you can sequence a unitary instruction. You could do classical controlled unitary instructions. So you have classical control in the CPU that decides whether or not to send this instruction V. In modern programming languages, they're starting to do these hybrid programs, as we've heard about a couple of times. So like Guppy from Quantinuum, they've worked quite a bit on this, where you have feedback back and forth. So you might do something like send an instruction to do a measurement. Then the measurement returns back to the CPU, enters the classical control flow there, and ultimately decides whether or not to sequence this unitary instruction W. The last one, the controlled Y, is something that you can't really do. And I'm being a little facetious when I say you can't do it, because, okay, it's a unitary. You can always just send it as a unitary instruction. But you know, in this coprocessor model, you don't really have quantum control flow. You just have classical control flow, which means doing this really as a controlled operation isn't really possible. There's been a fair amount of work talking about this in the last year or two. So for example, this paper, where you can read more about why upgrading classical models of control flow to quantum is not so easy. Okay, but then I'm going to talk about this circuit language, where we, among other things, we've got a generalization of this notion of controlled operations because we're interested in studying them. Why? Because, oops. Sorry, my computer went to sleep. Ah, there we go. Why? Because, well, those are kind of universal in circuits. I mean, people use them in algorithms all the time. Okay, so the first couple slides here, I'm just going to talk about the mathematical formalism. This comes from category theory. We're modeling circuits as prop. A couple people have talked about this already, so I go sort of quickly through it. But so this is just a way to describe what a circuit is. So in this prop formalism, You describe a language of, well, a language, so a family of circuits, basically as a collection of generators. These are just named boxes, so they have a name G and they have a signature N, which is just a number of input wires. You specify those, and then you also, of course, typically specify the semantics, which here is going to be unitary matrices because we're talking about quantum circuits. You always get these two for free. You get the identity wire and the wire crossing, which have these semantics. And then lastly, you have these two compositions, the sequential composition and the parallel composition that you use to basically construct circuits. And they have the usual semantics of matrix multiplication and tensor product or Kronecker product. I put U and V here because these are arbitrary subcircuits. So the idea here is that you construct the prop by just kind of freely composing with either the sequential or parallel compositions. So here's an example of what that looks like. This formalism was developed mainly by a group in Nancy. So this is the same gate set that is used by a couple of those guys. And yeah, the idea here is, okay, well, you have, like, for example, this generator H and this generator Z, which actually here is parametrized. So it's kind of an infinite family of generators, but that's fine. And because these are both in the language, you can compose them, and then that's now a subcircuit that's in the language. You can do the same in parallel. So these two are in the language, and this one is in the language. So the parallel composition of them is also in the language, and so on. And you basically just tile a circuit. So that's how the prop formalism works. What we did is basically slightly extend this. So we're using the same base prop, but then we're kind of adding two new compositions to capture some new stuff. So here they are. So they look like this. The first one here is meant to be subcircuit exponentiation. And semantically, it's just basically raising a matrix to a arbitrary real power alpha. I write it this way. I don't know if this is so familiar to everyone, but it's just exp is the matrix exponential, and then log is the complex matrix logarithm. I put a capital L here because it's putting every eigenvalue into the principal branch. That's a little detail, but it turns out to be relevant. And yeah, this is the first line there is really nothing new. I mean, that exists in literature. In fact, it even exists in practice. I think in OpenChasm 3, this was already implemented. There's something called the power modifier, and I'm pretty sure it's doing exactly that. So there, we're just kind of giving a name to something that already exists. The second line, I pause on a little bit because it's a little more new. So this funny thing is what I'm going to call the control product. And it looks a bit like a parallel composition in the sense that you take two arbitrary subcircuits on n qubits and m qubits, and you draw a vertical line between them. And it carries this semantics, which is okay, it's a bit strange. What we're doing is taking the logarithm of the two matrices involved, tensoring them together. We're dividing by IPi, which is just a kind of normalization, basically to return you to the principal branch. And then we're exponentiating the whole thing to get back to a unitary. And I'll show you in the next slide or two that this does, in fact, generalize the notion of a controlled operation. So this doesn't exist in the literature as far as I know. However, earlier this year, I was at QIP in Raleigh showing this as a poster, and Craig Gidney from Google came up to me and said, I recognize this. I had this idea back in 2017, and I wrote about it on a blog post, but never found anything to do with it. Oops. Never found anything to do with it. So this is a screenshot from that blog post, and you can see the definition is exactly the same. And he says, but I digress since I haven't found a thing for which the above idea adds clarity. So another way of looking at this talk is we're trying to find a way to use Craig Gidney's idea. Okay, then how do you actually construct this kind of modified prop with these two extra operations? The idea is basically the same. So in the previous version, we just kind of compose freely with the two operations. Here we do that as well, but then we also kind of compose freely in these two extra operations. So okay, what can you do? Let's do the exponentiation first because it's kind of easier. So here's some gate set that I'm taking as my base gate set. It's got, I don't know, this one that has no inputs and these two that have one input. and they have some names. So for example, since, I don't know, this gate is one of my generators, okay, I can do this, and it's also in the language. But then you can also exponentiate an arbitrary subcircuit. So for example, down here, I have some subcircuit that's composed of other stuff. There's a whole bunch of compositions in there. And that's in the language, and therefore I can exponentiate the whole thing to some power beta, which could be some user-specified real number. And that's also in the language. So that's how the exponentiation works. The control product is a little bit more interesting. Okay, first of all, you have things like this, where you can take two of the base generators and connect them with a vertical wire, do the control product, and that's something that's in your language. But then you can sort of nest these things. So, for example, in this dashed line, there's two boxes here that are being connected, and you can see inside here is a subcircuit that contains kind of a level 1 control operation. And that's where the name hierarchical comes from, only because you get this kind of hierarchy of nesting, and you can have this sort of nesting depth and so on. But anyway, because this is in the language and this is in the language, then the control product of them is also in the language. And then you can see there's even a third level here. I've got a big box here, and it's being connected to some other subcircuit there. Okay, so that's how that part works. That's the category theory construction, and now I want to tell you about some things that you can do with it, or sort of concrete examples. So first thing I want to show you is a universal gate set for quantum computing. So this is actually the same gate set that I had in the last slide. I've just changed the labels. So this one before was called -1 because it's semantically just the number -1. And then this one has a semantic of a Pauli Z gate. And this last one has a semantic of a Pauli X gate. If you exponentiate those three, then you get this stuff down here. So you get respectively global phases, Z rotations, and X rotations on the Bloch sphere. So if you know some stuff about quantum computing, you know that that's a universal gate set for 1 qubit, because you have 2 arbitrary rotations around 2 different axes. And then if you connect this thing here to an arbitrary subcircuit with this control product, you get, well, exactly what you'd expect. So most people would interpret this as a controlled U, and semantically it is a controlled U. So this is the sense in which these things strictly generalize controlled operations. But of course, you don't have to put this black dot. This could just be some arbitrary subcircuit on m qubits. So, okay, why does that give you universality? Because if I put in the X gate for U, just a 1 qubit X gate there, then I get this Z control product to X, which is a C naught. And then C naught plus an arbitrary a universal 1 qubit gate set gives you universality. Next, I want to show so recently there's been a couple papers talking about related things. So this year there was this paper which I think it's actually being presented in this conference, but not in PlanQC if I remember correctly. This is the Quantum Circuits Are Just a Phase paper by Hoynen and co-authors. So anyway, they have this primitive, which is, the idea is that you kind of select a subspace, and then you apply a phase in that subspace, and they show how you can use this to construct arbitrary controlled unitaries. And since we're generalizing controls, it's reasonable that there should be a connection, that we can rewrite what we're doing in their language. And this is showing what that is. So this is the property that makes it work. You have some arbitrary control product here, and there's this fact, which is at least semantically true, that if you can write U as a composition, a sequential composition of some circuits A, B, and then A dagger, where A dagger is just the reverse of A left to right and with all the powers negated, then you can kind of split the A's off on either side. And the only part that remains connected with a control wire is the middle section. That holds symmetrically on both wires, so you get this thing. And okay, so a particular choice of unitaries A and B that's kind of the most interesting one is the spectral decomposition, where A is some subcircuit that diagonalizes U. And so, okay, if I write U and V in their spectral decompositions, so in other words, U has these eigenvectors uj and associated eigenphases theta j, and likewise for V with eigenvectors vk and eigenphases rho k, then what this operation does in this if-let primitive from the Hoynen paper is this. It's essentially doing a switch case statement over the eigenbasis of U and V. And you'll notice that the things that it's, oh, not again, sorry. Yeah, the eigenvectors that it's selecting over are tensor products of the two, and that comes just directly from here. Basically from this you can read off that the eigenbasis of this control operation is the same as if they were just a parallel product. So it has a separable eigenbasis at the cut defined by the control product wire. And yeah, so it selects a space based on the eigenbasis, and then it applies a phase that's proportional to the product of the two eigenphases. These last two bits here I include just because, so okay, in the literature I would say it's folklore that people sort of know this stuff, but I think it's a bit under-discussed. What I'm pointing out here is just a general property of these control operations, and specifically also of normal controlled operations, controlled unitaries and so on. I'm writing here that there's this funny feature that the wires that are acting as the control and the wires that are acting as the target are actually arbitrary. So I'm just pointing that out here, that so in this one we're just kind of quote unquote interpreting the top wires as the control wires. So we're reading over the eigenbasis of U and applying operations on the bottom wire. And then at the end here we're doing the reverse. So we're considering the bottom wires to be the control wires, and we're doing operations on the top wire. But these are really all mathematically equal, so that's why I write equal signs. They're not like connected by some unitary transformation, they really just are the same thing. Okay, now I want to just talk briefly about some potential applications to, I don't know, compilers, circuit optimization, that sort of thing. So on this slide I'm showing a couple things that I've found in the literature recently that people have been using. So on this top line we have a circuit identity that's been used in a whole bunch of places, from high-level language design, like it was used in Quipper recently. There was this proto-Quipper with reversing and control paper that uses this. It also appears in low-level circuit optimization, like a paper by Vivian Vandel talking about shrinking adders into logarithmic depth uses this. And this one can be seen as a special case of the same identity that I showed on the last slide, where just the top wire is specifically like a 1-qubit Z gate. But I mean, in general, it can be, you know, m-qubit subcircuit. Speaking of that Vivian Vandel paper compressing adder circuits, this is the trick that ultimately makes it work. It's actually, we've seen the same circuit identity in some previous talks, even just rewritten a little bit. And well, like every identity that involves controlled operations, you can generalize this to the control product. Here it looks like this, where now these wires are n-qubit wires, and you have some n-qubit subcircuits, U and V. And this identity still holds, except with these conditions that basically tell you that U and V have to more or less mimic the Pauli algebra for this identity to hold. And then, okay, lastly, some little examples like this one showed up in a preprint from Craig Gidney like a month or two ago, where he has this funny notation with Z flags. Lots of people that do circuit optimization have their own custom notations, and this is one of them. And he gives a decomposition in terms of topheles and C-naughts, describing what this thing does. But in our language, it does basically this. So it's basically a C-naught that's controlled by a pair of Z gates that are not internally connected. So one way of reading what this gate does is it reads the top two wires in the parity basis, in the computational basis, and if it's odd parity, it does a C-naught on the lower two. If it's even parity, it does nothing. Okay, and then the last one is just like a cute little presentation of Grover, where we have like this is the phase oracle, where I've selected one particular marked state, and then this X gates all connected together is what people usually call the diffusion operator, and then we're exponentiating it, or repeating it the usual number of times. Okay, so that's the end of the talk, and now I'll take some questions. If I can move to the last slide here. Hello? Oh, there we go. Thank you.
Hi. Yeah. Do you have ideas of how to reduce these hierarchical control blocks to like standard quantum circuits?
Yes, the short version is we would need a diagonalization procedure, essentially. So I think it's going to be basic. Oh. Okay. It's fine. Well, anyway, I had that identity where you kind of split off sub-circuits. And
until you're left with a diagonal bit in the middle, and then you can do...
Yeah, once you have a diagonal bit, then you can reduce it just to normal, like controlled operations like people would normally think of. And so then the only tricky part is how to do this diagonalization. And obviously a dumb way to do it would be to like convert it into a matrix, diagonalize the matrix, and then synthesize a circuit. But that's definitely going to be inefficient because it's exponentially large. There probably is an efficient way of doing it because the circuit is kind of exponentially smaller, but that would involve diagonalizing something diagrammatically. And that's certainly something I'm interested in doing, but I have no idea how to do it. So if anyone has any ideas, please come tell me how.
Okay,
thank you.
Thank you very much. Sorry,
Now does it work? Okay. So first I'd like to thank the organizers for this wonderful workshop. There's been some hitches along the way, but it's very nice. So today I'm going to talk about my joint work with Robert on denotational semantics for stabilizer quantum programs. And the paper's on the archive, and I've implemented the denotational semantics. But first, Robert's not here today, but I want to give him a shout out. He's the postdoc in Oxford, really chill guy. People can attest to this. And for me, I'm a postdoc in POPL'26, and also I'm looking for a job if someone can hire me. So why do we need a stabilizer quantum programming language, and why do we need denotational semantics for this language? So my argument is that if we actually want to implement quantum programming algorithms, we need quantum error correction, because like quantum computers are they're very noisy and they're not very fault tolerant, so you need to use these techniques. And of these techniques, the most prominent is stabilizer quantum error correction. And stabilizer quantum error correction doesn't just use unitary maps. There's a bunch of different operations which are needed. So we need Clifford unitaries and stabilizer states. We need Pauli measurements, classical operations, and classically controlled Pauli corrections. So these are like the general basic building blocks of a stabilizer error correction protocol. So this motivates the talk. We want a programming language which is like native to the stabilizer formalism, and we also want a denotational semantics which exactly captures this, so that we can reason about, optimize, and verify such quantum error correction protocols. So here's like a kind of vague, rough diagram of what you might want to do for a stabilizer quantum error correction protocol. So you have some, unitary or isometry which encodes things, and then you perform a Pauli measurement, and you apply some classical operations, and maybe some error occurs, and you want to apply some corrections to fix the error. So this is our language, and we have all of these operations. So you can compose things, you can initialize a classical bit, you can apply some classical transformation, you can discard the classical bit. And also there's some quantum operations. You can initialize a qubit, you can apply a unitary, and then there's some, you can measure something and apply a classical control. So you can mix the quantum and classical. So before I get to the denotational semantics, I want to do a bit of exposition. So in quantum theory, there's kind of three stages which I'll build things in. You have pure quantum theory, and you can add mixed states to get to mixed quantum theory, and you can go even further by adding classical types. So mathematically, pure quantum theory is just like linear algebra over the complex numbers. And you can apply this abstract construction to obtain completely positive maps between finite dimensional matrix algebras. And there's another abstract construction you can apply, which gives you the same thing, but in terms of C-star algebras rather than matrix algebras. So I interpret the C-star algebras as your classical types if they're commutative. And for my purposes, I'm not going to care about mixed stuff because it will just, it's not useful for the exposition. So I'm going to go directly from pure state to mixed quantum computing with classical types. So this talk is all about stabilizer quantum programming. So I'm going to restrict my attention not to all pure state and mixed state quantum mechanics, but only those which are constructed using these operations I described. So you can apply the same abstract construction to pure stabilizer theory to obtain some stabilizer theory with classical types. And the denotational semantics which we're going to build starts with the observation that pure stabilizer circuits are equivalent to this category of relations over the finite field of characteristic P. And note that here on the left, the tensor product is given by the direct sum, whereas on the right is given by the bilinear tensor product. And the idea is by applying these same constructions, from which we go from pure stabilizer theory to stabilizer theory with classical types, we can do the same thing on the left and obtain an equivalent category. So I'm going to try to explain the semantics using examples. So in stabilizer quantum error correction, we interpret errors as Pauli matrices. So I'm using this kind of ZX notation. So for any numbers x and z mod p, we can build the Pauli operator like this. And I'm going to denote it like the Pauli x is red and the Pauli z is green. So we don't have to think of things in terms of linear maps, but we can just think of a Pauli as a vector. So it's even dimensional, and the x is on the left and the z is on the right. So you can define this notion of stabilizer states, and a pure stabilizer state is determined by which Pauli operators you can apply to the state which act trivially. So it's the things which are kind of invariant under these errors. And it doesn't matter which way you go, from this point of view, we can see stabilizer states as subspaces. So you take all of the Pauli matrices which do nothing together. It's not an element anymore, it's a subspace. And more precisely, it's what's called an affine Lagrangian subspace. So it's a subspace with really nice structure. And here's an example. Ket 0 is such a subspace where the x stabilizers are fixed to be 0 and the z stabilizers can be anything. And similarly for the plus state, you just do the opposite thing. So the z stabilizers are fixed to be 0 and the x stabilizers can be anything. But like I said before, we don't want to just have stabilizer states. We also need more complicated operations. So if you just have some pure stabilizer circuit, then you can determine it in the same kind of way as for states in terms of how the Paulis flow through the operator. So if you take the Paulis on the right and you take the inverse, then now you have pairs of Pauli operators which act trivially on the operation. So we can think of such a pure stabilizer operation as a subspace, where the input dimension is on the left here and the output dimension is on the right. And in fact, we can think of this not just as a normal subspace, but as a relation, because there's some direction to what's in the input and what's in the output. And again, more precisely, this is an affine Lagrangian relation. So here's an example, the discrete Fourier transform. It takes your stabilizers here, swaps them, and then negates the Z stabilizer. And what's really nice about this representation of pure stabilizer quantum circuits is that you can compose them using relational composition. So you have these two stabilizer circuits which you represent by relations, and you compose them by taking an element in the middle and taking the conjunction. And if you work with relations, then the composition is tractable, whereas if you just multiply the matrices naively, then it's exponential. So I talked about the pure stabilizer circuits, so now I'm going to move on to more complicated things like I described in the first slide. So how do we know if an error has occurred? We can't just use pure states. We have to go a bit further, and we have to perform measurement. So here we have our Z stabilizers and X stabilizers, and we're going to measure it in the Pauli Z basis. And what happens when you do this is you just forget the Z Pauli Paulis, and you get the X Pauli out. So we can think of this as a relation as well, and what it does is it takes the two stabilizers, the X and the Zs, and it just forgets the Zs. And we're going to annotate the quantum subspace with a Q, because here this is a classical wire, and here this is a quantum wire. So they're really two different kinds of objects. So now that we have pure state stabilizer computation and we have measurement, how do we actually correct against the errors? Well, we have to perform a classically controlled Pauli operation. So here is the Pauli X gate. And as we all know, if you apply ket 0 to the Pauli X gate, it does nothing. If you apply ket 1, it's an X gate. And more generally, if you apply ket n, then it's x to the power of n gate. So in terms of relations, it looks like this. You have here on the top, you have your classical dit, and then you have your X and Z stabilizers. And what this does is it takes the classical dit and just adds this to the X stabilizers. And you have this relation. So classical, quantum, quantum. So let's revisit this language that I described earlier. So all of the operations in this language were described on the previous slides. We have all of the classical things, the quantum things, and their interaction. But the question is, what is the denotational semantics of this language precisely? Like, what exactly do we generate? We have to ask one more thing, that the operations are physically realizable, which means that they have to be trace preserving. And in the relational picture, the trace corresponds to the relation, which just takes all of the X and Z stabilizers and just kind of throws them away. So this gives us the denotational semantics. So the operational semantics are the trace preserving mixed stabilizer operations with classical types. The denotational semantics is the total affine relations with this symplectic modality I described. And then the syntax is this stabilizer programming language. And all of these three things are equivalent. It's not like an embedding in one or the other. It's all exactly the same. So here's a big table with all of the denotational semantics. You have your composition, dit initialization, qdit initialization, your classical operations, measurement, nothing operation, quantum discard, controlled, classically controlled X and Z operations, and any Clifford unitary. With all of the types annotated. So there's some caveats which I swept under the rug. First, perhaps most annoyingly, is that all of this stuff only works for odd dimensions, and everyone cares about qubits, which is kind of a pain. But at least we can talk about qubits if we don't have access to the phase shift gates like the S gate or the Hadamard gate. So it's not everything, but at least it's something. And also, in our denotational semantics, we only have a linear control. We can't perform an AND gate on our bits. And we conjecture that if you add the AND gate, then the denotational semantics will detect the possible errors, but we'll forget about the probabilities. And when you're performing error correction, you don't care what probability an error has occurred with, but rather that an error has occurred or not. So that would be nice if we can prove it. And also, the language we gave is very low level. It's like an assembly language. So this is just more of a proof of concept. What would be really nice is if we can exploit this very nice, well-structured denotational semantics to build a more expressive syntax. You know, maybe have a type system which can tell us something about the properties of the stabilizer protocol. So can we verify or talk about fault tolerance within a more sophisticated type system? And yeah, basically the denotational semantics is exactly what people call the stabilizer formalism, and this is like when people are reasoning about stabilizer or quantum error correction codes, they're not usually thinking of the complex matrices themselves, but rather the tableaus and the subspaces and so on. So this is kind of like the native semantics for doing this specific kind of computation. And I'd like to thank my talk. Thank you for attending my talk. And in honor of Robert, this is his official photo on his website. I've just chosen a random bar. So because we're running a bit late, maybe still, I suggest ask me questions here at the Delirium Cafe.
The other way, it's at the bottom.
Here.
We are at the top.
Okay.
Thank you very much. We started and ended this session 10 minutes late. Thanks to the speakers for keeping to time. I will take your suggestion as permission to leave questions to the bar. So can we thank the speakers and the organisers for an excellent workshop today.